Hello everyone, and welcome to what will be our largest space tour ever on this channel. Tonight we're going to visit every planet of the solar system, starting with Mercury and Venus, the two innermost planets. They are the closest to the Sun. Don't worry at all if you are not familiar with astronomy. It is all going to be easy to understand with simple examples and explanations. But for now, in preparation for the long discovery journey that awaits us, please adopt a comfortable position. There is no problem at all if you drift and fall asleep. You can always return later. Let's get started. The first leg of our trip begins close to the Sun, near the smallest and fastest planet of the system, Mercury. Mercury is only about twice bigger than the Earth-Moon, and there are actually satellites that are bigger than it, like Ganymede, a moon of Jupiter that we will visit later, or Titan, a moon of Saturn. But Mercury is considered a planet because it follows its own orbit around the Sun. It is not the satellite of another planet. Its mass is also bigger than any of these satellites, because Mercury is denser. Its density is similar to Earth, and it is believed that Mercury is mainly made of metal, 70% of it, dominated by iron, and the rest, about 30%, would be silicate material, what we generally call rock. As we're going to see, conditions at the surface of Mercury are strongly influenced by the proximity of the Sun. But how close to the Sun is it exactly? In average, the distance is about 58 million kilometers, or 35 million miles. For comparison, the Sun has a diameter of 1.4 million kilometers, so it's actually not that close, proportionally. If the Sun was the size of a basketball, then Mercury would be a small grain of sand, but several steps away from the basketball. Still, this raises a question. Mercury is comparatively very small, and due to its mass, which is enormous in comparison, the Sun is a huge gravity well. So why does Mercury keep its distance with the star instead of being pulled to it and swallowed? This brings the question of speeds and orbits. Mercury travels in space around the Sun at high speed. Its velocity is 48 kilometers per second, about 30 miles per second. For comparison, Earth travels at 30 kilometers per second. A general rule is that the farther planets are from the Sun, the slower they are on their orbit. The farthest one, Neptune, travels at only 5.4 kilometers per second, almost 10 times less than Mercury. And this is not a coincidence, because an orbit results from an equilibrium. There are two main variables to consider in a star system like ours when it comes to orbits. There is the gravitational pull of the huge mass that is at the center, which pulls the planets. And there is their velocity, which tends to push them away. It is a centrifugal force. Without the mass of the star at the center pulling them, planets would just escape. Their speed would surpass escape velocity, that is to say, the speed above which they can break free from the gravitational pull of another body. Their orbits form thanks to this equilibrium. There are bodies that sometimes escape the systems where they appeared and travel between stars, sometimes even planets. We know there are lone planets, which most probably formed in a star system and were expelled from it. Because even though orbits can last for hundreds of millions of years, billions even, they can be altered by other bodies sometimes, that for example make a planet or a satellite accelerate and break free. The equilibrium also does not mean that the orbit is a perfect circle, or that the speed is constant. Most orbits are actually elliptical. They look more or less oval. And that's particularly the case with Mercury. When the planet comes closer to the Sun, gravitation tends to make it accelerate, which means that it is pushed away. Its higher speed allows it to go farther from the Sun, but not far enough and fast enough to break free from it. So after traveling following a curve that makes it move away, it is pulled back, it reaccelerates, and so on. The cycle repeats itself. In the case of Mercury, it repeats itself in 88 of our days. So the Mercurian year, one revolution around the Sun, is 4 times shorter than on Earth. Now, when we say that planets like Mercury revolve around the Sun, it works and it is a statement that can be considered true. But it is not 100% accurate. What the planets and everything in the system revolve around is not the star itself, but the center of mass. The Sun accounts for more than 99% of this mass, 99.8% to be precise. So obviously it determines very strongly the center of mass. But the real center of mass in the system is not the center of the Sun. Each planet also has a little gravitational pull and drags the center of mass towards it. Of these planetary influences, the most important one in the solar system is by far Jupiter, because it is the most massive planet. It is more massive than all the other planets combined. Now, as it happens, the center of mass is generally inside the Sun, because planets are scattered around it, so their respective pools tend to cancel each other. But sometimes the center of mass can be outside of the Sun. If we imagine an extreme case, for example, when all planets are on the same side of the Sun, and they all pull more or less in the same direction, which is something that can happen. If all planets were to be aligned on the same side, the center of mass could be at a distance of 2 suns' radius from the Sun, 1 diameter. It is not much, but it leads to another geeky question. How often, if ever, are the 8 planets of the solar system aligned on the same side of the Sun? Actually, extremely rarely, and technically they cannot be perfectly aligned because their orbits are not exactly on the same plane. They are slightly oriented, tilted. So at no point could we draw a straight line that would go through the centers of each planet because of the differences in planes. But if we simplify and just ask for the planets to look aligned, watching the solar system from above, you're going to see it probably never happened and is unlikely to happen before the solar system disappears. Why? Because an alignment of just the three innermost planets of the system, Mercury, Venus, and Earth, happens only once every 40 years. The chance to have Mars, the fourth planet, on the same arc at this precise moment is very small, and the alignment of the four first planets can only happen once every several thousand years. And as you add more planets, Jupiter, Saturn, Uranus, Neptune, slower and slower, with larger and larger orbits, the probability that they are all in the same arc at the same time decreases very fast, or, in other terms, the number of passes you have to wait for this alignment to happen increases exponentially. I found a paper by a mathematician who calculated that the alignment of the 8 planets could only happen once every 400 billion years. But the solar system is thought to be only 4.5 billion years, almost 100 times less. And the universe would be less than 14 billion years old, following the Big Bang theory. So it is unlikely that the alignment of the 8 planets that can happen every 400 billion years ever took place in the first 4.5 billion years of the solar system. Maybe the odds are around 1%. And the odds are also that it will not happen before the Sun dies and the system disappears with it. But still, the point was to tell you that the center of mass moved a bit over time, and that this is the real pivot around which planets revolve. Now it is time to take a look at Mercury itself. Like other rocky planets, it has a solid crust and a dissociated structure inside, meaning that elements are organized in layers with a mantle and a core. And as you approach the center of the planet, pressure and temperature increase. I told you earlier that Mercury was 70% metal. It contains proportionally a lot more iron than any other planet in the solar system. And this is a bit of a mystery, because why would a particular planet accumulate a lot more iron than others in its formation process? Rocky matter in the solar system had a certain ratio of silicate and metal that can also be found in rocky planets like Earth or Mars. So why does Mercury differ in its composition? The first theory to explain this, the most widely accepted at this point, is that Mercury was bigger than it is now in the past, several billion years ago. At the time, its mass would have been more than twice its current mass, with a metal-silicate ratio similar to other rocky planets. But the solar system was still in its early stages, and there would have been a collision with a planetesimal, that is to say, a fairly large object formed by the accretion of rocks and dust that crossed Mercury's trajectory. Based on models, this planetesimal would have been several thousand kilometers across, and about 1/6 of Mercury's mass. The collision between the two would have been cataclysmic, and would have ejected in space, stripped away, much of the original crust and mantle of the planet. That is to say, its rocky components. So Mercury would be so rich in metal, not because it attracted some more than other planets, but because it used to be a bigger planet that lost much of its rock and kept its metal. But this is just a hypothesis, and there are others. The second one has the same starting point. Mercury was more than twice more massive in the early stages of the system than it is today. But the loss of its rocky material would not have come from a collision, but rather from solar activity. The proto-sun, which was still forming, would have been larger than today. Gravitation made it contract to its current size over millions of years. So the Sun would have been larger at the time, and as a result, temperatures near Mercury would have been around several thousand degrees. This would have vaporized the rock at Mercury's surface, forming an atmosphere of rock vapor. And this atmosphere would have been lost, carried away by the solar wind, that is to say, the stream of particles that the Sun produces. So, a different explanation for the loss of Mercury's rock that would explain why it contains so much metal proportionally. A third hypothesis proposes that Mercury formed as a metal-rich planet from the start, because also of its proximity to the Sun. The huge cloud of gas that would have become the Sun would have caused drag on the particles from which Mercury was forming, was accreting. This would have made lighter particles go away, swallowed by the Sun, instead of being gathered by Mercury, whereas heavier metallic particles would have remained available, and as a result, Mercury would have ended with more metal than rock in its structure. In any case, this happened several billion years ago, and today Mercury presents a surface that is similar in appearance to that of the Moon, with large plains and a lot of craters, which always indicates that the body is geologically inactive. The surface material is not renewed by volcanism or plate tectonics like on Earth, but instead it stays still, and only impacts from asteroids can modify its appearance. Due to the proximity of the Sun, it makes sense to anticipate high temperatures at the surface. And indeed, this is the case, but only on the parts that are directly exposed to the Sun. Mercury can also be an intensely cooled place. Near the equator and during daytime, on the side of the planet exposed to sunlight, temperature rises up to 700 kelvins, that is about 800 degrees Fahrenheit, and more than 400 degrees Celsius, about twice the temperature in a cooking oven. But the same regions, at night, when they are plunged in the dark, fall to 100 kelvins only, that is minus 280 Fahrenheit or minus 173 Celsius. That is to say, cold enough to freeze water instantly. I'll tell you later about the conditions on Mars. They are harsh, but they are almost welcoming in comparison with that. And to make it worse, a day or a night lasts a very long time on Mercury. The planet revolves fast around the Sun. I told you before, 88 days. But it rotates, it spins slowly on its axis, and in a way that is locked to the Sun. Every time the planet completes 2 revolutions, 2 orbits, that is to say 2 Mercurian years, it rotates 3 times on its axis. For comparison, when the Earth completes 2 orbits, 2 of our years, it rotates more than 700 times on its axis, 2 times 365. But Mercury only 3 times. It is very slow at rotating. Another way of saying it is that one single rotation of Mercury happens in 58 of our days. But it also means that any point on the equator of Mercury can remain exposed for a very long time to the Sun, or for an equally long time stay in the dark, 176 days, 2 Mercurian years. The solar day, the time for the Sun to rise, stay in the sky and set, is actually longer than a year, due to this combination of rapid orbital velocity and slow spinning. 1 year on Earth is a touch more than 365 solar days, but on Mercury, 1 year is half a day. There are also regions of the planet around the poles that are constantly in the dark, or almost in the dark, and where the temperature never rises much. Probes that were sent in the past decades have shown that there was ice, probably water ice, that stays frozen around the poles of Mercury. This shows that despite its proximity to the Sun, the planet is not just a burning hot desert of plains and craters. The hottest planet of the solar system is actually not Mercury, but Venus. If you find Mercury hostile, wait for Venus because it is worse. So let's go on with our journey to our second destination, and also the second planet from the Sun in the solar system. At first sight, Venus and Earth could look like twin planets. Almost the same size, Earth is just a touch bigger. They are not that far apart, and actually there may have been a point in the distant past when Venus looked more like Earth than today. But nowadays the conditions at their surfaces could not be more different. We saw before that Mercury was at 58 million kilometers from the Sun. This is just an average because its orbit is elliptical. Venus is at 109 million kilometers, almost twice as far. The orbit of Venus is comprised between the Sun and the Earth orbit, and this means that seen from Earth, Venus is never very far from the Sun, and when it is not hidden by the Sun's light, it is not hard to see. After the Sun and the Moon, it is the most visible, the brightest object in the sky. And it is visible not just because of the relatively short distance on an astronomical scale, but because of a layer of very reflective clouds in its upper atmosphere. Mercury, the Moon, or Mars barely have an atmosphere compared with Earth. But on the contrary, Venus has the thickest, densest atmosphere of all rocky bodies in the solar system. The clouds that block sight and make the planet look white seen from space are composed primarily of sulfuric acid. But this is just a taste of what lies beneath. The atmosphere is so dense that at Venus' surface, pressure is more than 90 times what it is on Earth. For comparison, it is equivalent, the pressure, to being about 3,000 feet, 900 meters, underwater. That's a pressure human bodies cannot stand, obviously. Now there are submarines that reach this depth and more, so it is not impossible to imagine a man-made vehicle resisting to the pressure on Venus. But the other problem would be heat. The mean temperature at the surface is estimated at more than 700 kelvins, that is 460 degrees Celsius or 870 degrees Fahrenheit, actually hotter than the surface of Mercury when it is exposed directly to the sun. Why is Venus so hot? Also because of the atmosphere. We'll come back to the reasons why Venus ended up with such a dense atmosphere, but if we look at what it is now, it is primarily made of carbon dioxide, 96% of it, plus 3 to 4% of nitrogen, and traces of other elements. We know it rather well because Venus was one of the first targets of space exploration. The Soviet Union had an ambitious program to explore this planet in the 1960s, and they sent several probes. These probes didn't survive long in the atmosphere, given the conditions, but long enough to send a lot of valuable information. And since then, more and more information about Venus has been collected, including with a NASA probe called the Magellan Orbiter. This probe was able to map the surface with radars, since it is hidden in visible light. The carbon dioxide at the surface is in a state that we don't normally encounter on Earth. It is called a supercritical fluid. This means it is not just gas, because it is very pressurized, also very hot, but not to the point of being solid. It has passed the critical point of pressure and temperature where it could be a gas, but there is not enough pressure to make it solid, so it exists in an intermediary state beyond the gaseous and liquid phases. It is this state of matter that is called supercritical fluid. It is believed to be rather common in the atmosphere of gas and ice giants, Jupiter, Saturn, Uranus, Neptune, and also on Venus. On Earth, it doesn't normally occur naturally because of the different set of conditions, except maybe for water at the exit of some hydrothermal vents. Hydrothermal vents are like natural chimneys that eject very hot water, heated by the temperature from the Earth's mantle. But they eject this water deep underwater. So when it comes out of the vent, this water is very hot, several hundred degrees. So at surface conditions it would be steam. But it cannot be steam because there is too much pressure for that. We are deep underwater. It cannot be just liquid either. It is too hot for that. And at the same time there is not enough pressure to make it solid, to turn it into ice. So it is in a supercritical state. Not for long, because it is ejected in water that is much colder, so it cools down quickly and becomes just liquid. It is hard to imagine the texture of a supercritical fluid. We are not used to it at all. But in any case, you don't want to experience it, because if you plunged your hand into a supercritical fluid, it would be at the same time burned and crushed. This gives you an idea of the kind of environment at the surface of Venus. And Venus' atmosphere is also responsible for the heat. It is so dense that it doesn't let any heat escape. It is a massive greenhouse effect, but extreme, the strongest we know of in the solar system. Venus did not form with such a thick atmosphere. Typically, the gases that compose the atmosphere on a rocky planet can come from asteroid impacts. They are liberated and stay because of gravitation, or they can come from degassing from the planet's crust and mantle. That is to say, when gas is released at the surface, typically what happens with volcanoes. This atmosphere stays in place around the planet when the planet is massive enough to retain it due to gravitation, and when it is not carried away, ejected into space by collisions or by the solar wind. A magnetic field, like Earth, also helps retain it. Venus does not have one, so gravitation explains how the atmosphere stays with the planet. Earth and Venus have similar masses. I told you Earth is just a touch more massive. So they also have quite similar gravitational pulls. Given this set of conditions, why did Venus ended with this crushing atmosphere and Earth did not? These are just hypotheses, but studies have suggested that several billions of years ago, Venus could have had an atmosphere rather similar to the early atmosphere of Earth. In these conditions, there could have been substantial quantities of liquid water on the surface, and why not? Life could have appeared in these oceans if they existed. But what would have doomed Venus would have been its proximity to the Sun. The distance from the Sun to Venus is 70% of the distance from the Sun to Earth. This means more energy received from the Sun. And as in the first 100 million years of the solar system, the Sun gained in luminosity, this water on Venus could have entirely evaporated. This would have accumulated greenhouse gases in the atmosphere. Water as gas, as vapor, has a greenhouse effect, and once past a critical point of greenhouse effect, the heating of the planet would have snowballed into a loop. The accumulation of heat at the surface liberated even more greenhouse gases, thickened the atmosphere, and made it even hotter, and so on. At this point, it is hard to imagine life at the surface of Venus. But if there is some, and this is purely speculative, we have no solid evidence of life on Venus at this point. It could be not at the surface, but higher in the atmosphere, in the upper cloud layers of Venus, about 30 miles, 50 kilometers up from the surface. Because there, temperature and pressure are lower, and actually not that far from terrestrial standards. But this environment is also very acidic, so the forms of life in that environment, if they exist, would have to be able to thrive floating in a type of environment that has no equivalent on Earth. Actually, these clouds are so dense that things could float on them. Venus was one of the first sources of inspiration for terraforming, or at least the installation of human cities on other planets. We will expand on that when I tell you about Mars and terraforming. Another effect of the atmosphere that completely surrounds the planet is that the temperature is about the same everywhere. There are no large differences between the equator and the poles, like on other planets. But there are still differences in temperatures because of differences in altitude. Venus has a geography with plains. They cover 80% of it, and they have a volcanic origin. There are also apparently active volcanoes on Venus, and this sulfuric acid we talked about in the clouds of the upper layers of the atmosphere would come from them. There are highlands, impact craters too, no small craters, because it takes a big asteroid to cross this atmosphere and impact the surface. Many meteorites, like the ones that sometimes hit the Earth's surface, would be destroyed and vaporized long before it happens on Venus. But there are larger impact craters left by bigger asteroids. The images we have from the surface are not actually photographies. They are radar maps that have been colored in false color. But they still give an idea of what the surface looks like. A surface probably similar to what the Earth would look like, with no water, no life of any kind, and constantly plunged in darkness because the sunlight cannot reach the surface. There would be many more things to say about Venus, but we have so much to discover around the solar system. So for now, we're going to return to Earth because its orbit is on our way to the next destination, Mars. Earth is already getting smaller, and we have crossed the orbit of the Moon. But there are still millions of miles to cross before we reach Mars. In past space cruises, we had to travel faster than light to reach exoplanets and even other galaxies. Such speeds defy the laws of physics as we know them, and there is good reason to estimate that they cannot physically be achieved. But tonight, traveling at a few percentage points of light speed will be enough to complete the round trip in about 1 hour. Such a speed has never been reached by man, but it is theoretically possible at least. So, what is the distance between Earth and Mars? There is not a single answer to this question, because the distance is constantly changing. Since you tuned in to this story, the distance has changed by thousands of miles, as the two planets follow their orbits around the Sun at high speed. Sometimes they are on either side of the Sun, and when this happens, Mars is invisible from Earth. When the two planets are on opposite sides of the Sun, the distance is maximal and it reaches 400 million kilometers. This would be like 10,000 times the circumference of Earth. But there are also times when Mars is much closer. When Earth and Mars are aligned on the same side of the Sun. In this case, the distance drops to about 55 million kilometers, almost 8 times less. This is less than 40 million miles. About every 26 months, Mars reaches this close approach, this is how it is called, to Earth. And this is the right moment to take advantage of, to send missions to Mars. But the distance when a close approach happens is not always exactly the same, because it is not that simple. The two orbits of Earth and Mars are not exactly on the same plane. They are slightly tilted with respect to each other, and the exact shapes of these orbits change constantly because they are influenced by the position of other bodies, especially Jupiter, which has a significant influence on the orbit of Mars. At the scale of the solar system, these changes in orbits are very small, but they are absolutely relevant to space travel because they imply differences of hundreds of thousands of miles. The precise calculation of where planets will be is nothing new. It was developed along the 20th century and became crucial when probes started to be sent to space. But you can imagine the complexity of the observations and calculations that have to be made to take into account velocities and the influence of all bodies involved. So there's a lot of modelizing and mathematics going on to make accurate estimates, because a probe cannot miss its destination, which is constantly moving by millions of miles. And this is what would happen without good knowledge of orbits, speeds, and all the factors that impact them. So with all these elements at play, not all close approaches between Mars and Earth are exactly the same. In 2003, Mars made its closest approach to Earth in 60,000 years, and it won't be that close again until 2287. In the meantime, we will have to cross a bit more distance when close encounters happen. But as I said, there is one about every 26 months, every 2 years. The last one was in 2020. The next one will happen in 2022. And there is already a next NASA mission planned. If not in 2022, then when the next close approach presents itself, a mission known as Mars Sample Return, a campaign to bring samples of Mars soil and rocks back to Earth. Given that probes or spaceships need to come back, these missions need to be planned over several years. It is not possible to just arrive, land, take samples during a few weeks, and come back immediately. Because during the time spent on the planet, the distance with Earth has increased again by millions and millions of miles. Now, the distance and time in space are not the only elements that matter. Energy consumption to go, land, and come back is maybe even more important. And the shortest trip is not necessarily the most realistic or achievable. Storing energy, fuel, is complicated. It occupies space. It has to be sent to space. And as soon as spaceflight began, astronomers and engineers started studying the most efficient path into space when it comes to energy consumption. An economical way of traveling between planets is to jump from one orbit to another, following an elliptical orbit. This kind of transfer is called Oman transfer orbit. This is the orbit followed, for example, by the InSight probe sent by NASA a few years ago. It implies approximately 9-month travel time from Earth to Mars, then a stay of about 16 to 17 months on Mars, waiting for the next transfer window, and another 9-month trip to return to Earth. That is to say, 3 years in total for the round trip. A method that can help consume less energy when approaching the target, the planet, is called ballistic capture. What is it? When spacecrafts use Oman transfer orbit, it typically requires the spacecraft to burn fuel in order to slow down at the distant planet. Because when the ship approaches it, it travels faster in space than its destination. It has to catch up with it. The fuel necessary to slow down has to be transported all the way from Earth, which adds to the cost and complexity of the craft. But with the method of ballistic capture, the spacecraft is just placed in advance on the orbit of its destination planet before the planet arrives. When the target arrives, the craft is captured by the planet's gravity, and it can put itself in orbit around it with small thrusters for adjustments, but without a big expense of energy. Now, another possible method to slow down spacecrafts when they reach their target is a maneuver called aerobraking. Aerobraking consists in flying the craft through the atmosphere, so it has to be a body with an atmosphere, at the low point of the orbit. The frictions, the drag, slows it down, and the advantage is that this method uses the environment. It doesn't consume more energy than the minimum necessary to position the craft on the right orbit. So all this gives you an idea of the variety of mission plans, of possible paths that have been imagined and tested. We are now halfway to our destination, so before we talk about landing and the environment we will find on Mars, let's take a look at the formation of the planet and what it is made of. As you may know, the dominant theory about the formation of planets in the solar system is that it all started with a large accretion disk, a disk of gases and dust that was kept together and put in motion by gravitation. Most of the mass of matter concentrated in the center to form the Sun, but not all of it. The periphery of the new star was still filled with matter, with dust, in orbit around it. And through collisions over millions and millions of years, this dust snowballed into bigger and bigger rocks and boulders. After millions of revolutions around the Sun, bigger rocks and protoplanets progressively cleaned up their orbits of dust and smaller bodies by absorbing them or turning them into their satellites. Like for Earth, this process is believed to have been completed about 4.5 billion years ago for Mars. At this point, rocky planets in the solar system had eliminated most of the smaller rocks and boulders on their orbit, and they had taken a ball shape. This globe shape happens because of gravity. Above a certain size, bodies become round, whereas smaller objects like asteroids or comets can keep other shapes. They are not large enough and massive enough to form a ball of matter. It is hard to figure out the history of Mars from Earth. On our planet, we can study the geological timeline by analyzing the layers of rocks and minerals. On Mars, nothing like that has been made yet. A few samples of soil could be analyzed by probes, but nothing comparable. But it doesn't mean hypotheses cannot be made. The age of the surface of a planet can be estimated by counting the number of visible craters. A higher number and density of craters points to older terrain. But Mars also has experienced intense volcanism along its history, and volcanism resets the surface terrain. It also has glaciers, winds, possibly running water in the past, so craters may have been erased. With these limited means of estimating the age of the surface, the oldest part is believed to be in the southern hemisphere. The surface there would be about 3.8 billion years old. In the northern hemisphere, the landscapes are dominated by large plains that would have appeared later, after the last waves of bombardment by asteroids. It is believed that after its formation, for about 400 million years, that would be 4.5 to 4.1 billion years ago, Mars had a dense atmosphere, which formed as a result of asteroid and comets' impact and gases escaping from the mantle of the planet. This early atmosphere would have been much denser than ours on Earth, implying higher pressure, and under these conditions, the water vapor in the atmosphere could have condensed into an ocean, possibly even a global ocean, but one that existed at high temperature, a little bit like in a pressure cooker. Slowly, over millions of years, this large body of water started to cool down, and this could have opened the first window for the possible emergence of life around 4.4 to 4.3 billion years ago. But this is purely speculative and based on modelizing. There is no direct proof of it. In any case, this early atmosphere would have lacked stability, because as the planet kept cooling down, it would have escaped into space or become incorporated into the surface. After liquid water and high pressure, the atmosphere would have become thinner and thinner, and the planet increasingly cooled as a result, turning water into ice. The following 400 million years, from 4.1 to 3.7 billion years ago, saw new drastic changes. Bombardment by asteroids could have kept happening like on Earth, and the southern hemisphere, the surface in the southern hemisphere, would date from this period. Like on Earth, Mars probably has a liquid core made of primarily metal. Metals tend to converge to the center of planets due to their higher mass. The core is covered by a mantle and a much thinner solid crust. In average, this crust today would be around 50 kilometers thick, to be compared with 40 kilometers on Earth. Once again, this is an estimate that looks possible, reasonable, but contrary to Earth, it could not be proven directly and by multiple methods. But at the time, 4 billion years ago, this crust was much thinner, and the planet had a period of intense volcanic activity. Great volcanoes appeared. After our landing, we will pay a visit to one of them, Olympus Mons, and fracturing of the surface made a large rift valley system appear. As a result of this volcanic activity that poured gases and ashes into the atmosphere, the planet would have stopped cooling down because the thicker blanket of gases trapped more solar heat, a greenhouse effect. At this point, clouds probably developed, and with them, precipitations running to the ground. This could explain the valleys that were possibly dug by running water billions of years ago, by erosion. And at the time there could have been also lakes forming in basins and craters. Maybe also an ocean covering the north of the planet. A clue that points to such a scenario with the existence of an ocean, or at least running water, is the analysis of rocks on the surface by rovers. They indicate the presence of clay minerals that typically form by prolonged exposure to groundwater. During this second period, another window for the possible emergence of life, the second one, theoretically opened. There was liquid water, an atmosphere, and also maybe a magnetic field around the planet like on Earth. The inside would have been in motion like on Earth, creating a magnetic dynamo that would have shielded the planet from radiation. In theory, this would make several of the conditions that allowed the appearance of life on Earth possibly present on Mars at the time. But again, these conditions didn't last more than a few dozen million years. Mars is a smaller planet than Earth, and it cooled down faster. As a result of it, the magnetic dynamo would have shut down, and the magnetic field would have disappeared. But more preoccupying for the possibility of life at the surface is the fact that atmospheric conditions continued to change. With its smaller mass than Earth, and without a magnetic field, Mars kept losing its atmosphere that dissipated into space millions of years after millions of years. What remained of the atmosphere started to cool down again, And with the accumulation of gases like sulfur poured by volcanoes, rains would have become increasingly acidic along a period of 800 million years, until about 3.6 billion years ago. Once again, this hypothesis is supported by the analysis of soils that were apparently altered by acidic groundwater. As the temperature went down, much of the water would have frozen, possibly under the surface. Bombardments by asteroids that had become less and less frequent over hundreds of millions of years almost came to a halt, like on Earth at the same time and in the rest of the solar system. Maybe punctually there were still asteroid impacts that melted huge quantities of subsurface ice and caused catastrophic floods that could only be short-lived because the water was reabsorbed into the ground and frozen again. After 1.5 billion years of catastrophic reverses in its appearance and atmosphere, Mars would have then entered a period of relative stability that continues to this day. Stability in the sense that there were no more large-scale geological changes or climatic changes. The surface of Mars was now dry, not much stayed of its previous atmospheres, and the new atmosphere has become so thin that there is very little pressure at the surface, so few that water vaporizes instantly at the surface. There can no longer be a liquid water. Over 3 billion years, there was still erosion with powerful winds. Occasionally, volcanoes appeared and modified the surface, like they do on Earth. But there doesn't seem to be plate tectonics like on Earth, and the face of Mars may not have changed radically for a very long time now. Seen from space, it has this red color that comes from the oxidation of iron. It is rust that gives Mars its name of red planet. The poles remain covered in ice, and the size of these ice continents at the poles probably varies over very long periods, depending on the distance from Mars to the Sun. I will tell you more about the conditions at the surface, but it is now time to land because we have reached our destination. We made this journey quickly, but for astronauts it will take months. Astronauts have already spent extended periods of time in space, including more than the time necessary to reach Mars. But it was in space stations that stayed on a low orbit around Earth. The psychological burden of knowing you are traveling further and further away from your planet in a potentially dangerous adventure in an environment where only technology can keep you alive, this cannot be looked over. This probably recreates the experience of the explorers who left Europe by sea in the 15th and 16th centuries, with their crews at the mercy of unpredictable oceans for months. There were situations of mutinies or despair. Now this human factor can certainly be overcome by selecting highly trained astronauts and making sure their group dynamic works for the mission. But the psychological and social dimension of such a journey, it brings challenges that cannot be fully eliminated. And then there are biological, physical difficulties. human bodies have not evolved for life in space, and especially in a zero-gravity environment. It is not just the loss of bone or muscle when we don't need to compensate for gravity for an extended period of time. There are other aspects that affect metabolism and the way our bodies heal. For example, it would be more difficult to treat a fracture without gravity. And this is also something astronauts would need to pay attention to. They could not really afford to hurt themselves. But the biggest medical issue in space is certainly radiation. On Earth, we are shielded from radiation by our magnetic field and the atmosphere. The radiations we talk about here are streams of tiny particles, bits of atoms, or of energy that exist in space or come from the sun. The sun ejects them constantly in every direction, and they travel through the solar system. This is a big problem for extended stays in space, because it is hard to fully shield against them, including inside spaceships or stations. One day spent in the International Space Station, for example, is equivalent to roughly 10 sessions of chest X-rays. If it is for a day or two, there are no measurable consequences. But when it is for months or years, the damage to the DNA, to eyes, to the immune system can become concerning. It is more than enough to significantly raise the risks of cancer, and the ISS is far from being the worst place in space. It is on a low orbit and still within the Earth's magnetic field, so traveling further in space will imply higher doses of radiation. An even more insidious effect of radiation exposure is that it may affect cognitive function over time, making astronauts maybe less able to respond to unforeseen circumstances or stressful situations. So, what can be done to minimize the problem of radiation? There are vests under development made of materials that are efficient at blocking free particles like protons. For example, vests made of polyethylene. Polyethylene is easy to make, it's a plastic. We use it all the time. This is the material of bottled water. There are radiation sensing instruments that could alert astronauts when they go through a place where radiation is more intense, and they could move to a part of the craft where they are better shielded. Metals that make the hulls of spacecrafts are not good at stopping radiation, but other materials are. Apart from polyethylene, hydrogen works well, and it would be possible to integrate hydrogen-rich materials into the spacecraft's structure, or maybe just align the walls with water tanks. Now, these options also raise issues of weight, because all this has to be sent into space. Another solution being explored by scientists, and it sounds a lot like science fiction, is to give the craft its own electromagnetic field, generated by a device on board the craft. It is probably for the long term, and it creates other problems like the energy necessary to make it work constantly. But that would be an ideal long-term solution to the problems of radiation for space travel. Because until such a solution is found, long-haul space travel with astronauts will be hard and a direct threat to their health. One day in space, outside the magnetic field of Earth, is equivalent to about 700 days on Earth when it comes to the dose of radiation received. It's almost like 2 years in a single day. In other terms, in 1 month in space, outside the Earth's magnetic field, astronauts receive almost the equivalent to a lifetime of radiation on Earth, if they are not protected. At this point, the issue of shielding against radiation is one of the biggest stakes for scientists who work on future manned missions to Mars or beyond. But we have now reached the proximity of Mars, and the first leg of our trip is done. Sometimes there are storms of dust on the planet that can reach global dimensions and completely hide the ground. This is one of the difficulties of the harsh environment we will find at the surface. But not today. Through the very thin atmosphere of the planet, we can directly see the ground and its variety of plains, craters mainly in the southern hemisphere, mountains, rifts, all in various shades of red to brown, except the wide caps of ice at the poles. These caps are primarily water ice, but not only. They also contain frozen carbon dioxide. Like Earth, Mars has seasons, because the planet rotates on an axis that is not perfectly perpendicular to its orbit, so it does not always present the same side to the Sun. When it is summer for one hemisphere, for one pole, that is to say, the pole receives direct sunlight, it is winter for the other one that stays in the dark for months. Without an atmosphere that regulates temperatures like on our planet, the dark pole becomes extremely cold for months, so much that carbon dioxide in the atmosphere freezes and falls to the ground. This covers the dark pole with a layer of carbon dioxide ice. But then, when the summer arrives, sunlight sublimes carbon dioxide. That is to say, it turns it instantly from solid to gas. Carbon dioxide liberated as gas brings dust with it in the atmosphere, and clouds form, clouds that look like cirrus clouds on Earth. Until the next change of season, when carbon dioxide freezes again and falls back to the ground. We will keep exploring the surface, but now let's land. We will do it like probably the first human missions will, landing in a rocket that will be able to take off at the end of the mission, return to the spacecraft left in orbit around the planet, and start the trip back to Earth. A dozen small crafts have already landed successfully on Mars since the 1970s. There was Mars 3, sent by the Soviet space program, and Viking 1 and 2 by NASA. Then there was a long period when funding issues and other priorities put missions to Mars on hold. They resumed 20 years later, in the 1990s, with the appearance of rovers like Sojourner, Opportunity, Curiosity, and more recently Perseverance, which landed in February 2021. Between these missions that have collected samples, sent images from the ground, and the cartography made by probes in orbit, our knowledge of Mars has increased, has improved dramatically in the past 40 or 50 years. And clearly between these successful missions and the various long-term projects for manned missions from public and private agents that exist at the moment, Mars is a hot topic in the world of astronautics. A human mission is unlikely to take place this decade, but the next, why not? And this raises the questions of knowing whether it is worth it or how much it would cost. Because apart from the risks of failure and the huge complexity, an obvious limiting factor is the cost. It is estimated to roughly $500 billion. This is a lot, or not that much, depending on how you look at it. If you compare it to the world's economy, $500 billion is not that much. The world's GDP is 87 trillions. So half a trillion would be 0.6% of 1 year of the world's economy. In other terms, it is equivalent to 2 days of economic activity on Earth. As a species, the perspective to try and go to another planet for the first time ever, for the equivalent to 2 days of work, it doesn't seem that much. And it can also be argued that this spending is also an investment for a part. This is the kind of projects that need research in materials, processes, fuels, equipments of all sorts that could have other beneficial uses. But still, this amount is well above the budget of any space agency or private investor. And it would certainly not be profitable financially. There are resources that could be exploited on Mars by a human community living there, like water, metals, and maybe many other materials to be discovered. But there is probably no treasure to find. It would be for the sake of knowledge, for science, for the challenge itself, or the perspective to one day establish a permanent human presence on Mars. It has been argued that this last point made sense as a species for humankind. A presence on different planets strongly reduces the risk of extinction, if we wish to consider this a goal. Because apart from that, there are plenty of places on Earth that are currently unpopulated by man, and that would be much easier and cheaper to colonize, like the poles and Arctic regions, deserts, or even the bottom of the seas. Each are inhospitable, but they are still way more welcoming than Mars for us. Even in the terrible cold and lack of vegetation of the Antarctic, for example, where the only human presence is scientific basis. At least there is air to breathe. There is pressure, so you can go out without a pressurized suit, and the temperature is actually almost pleasant if you compare it with Mars. The atmosphere is too thin to retain heat at night, and it is farther away from the sun than Earth, so the average temperature is minus 60 degrees Celsius, which is minus 80 degrees Fahrenheit. At best, the temperature near the equator during the day can rise up to 20 degrees Celsius, 70 Fahrenheit. It doesn't sound too bad, but in the same location, the temperature at night will drop to minus 73 Celsius, minus 100 degrees Fahrenheit. There is no place on Earth where the temperature varies by 100 degrees in a single day. Add to this the absence of air, the atmosphere is 100 times less dense, and it is 95% carbon dioxide, so there is nothing to breathe for us. The problem of radiation, the dust storms that can rage for weeks. This is actually very harsh, and any human community would have a precarious situation, living only thanks to their equipment. They would probably need to find shelter underground, or at least under anti-radiation domes, and they would desperately need to find water from which they could extract oxygen and irrigation for food production. They would also need to produce energy, probably with solar panels, and this is also a risk if the sun is hidden by dust for an extended period of time. They would have to pressurize the place where they live. These represent many elements of risk, and they could not afford to fail on any of them. Now, for the same amount of funding, it would be so much easier to create an entire underground or underwater city on Earth that could exist and function completely cut from the rest of the world. It doesn't sound useful, and no one is going to invest in this, but if the argument in favor of establishing bases on Mars is to gain living space, or compartment humanity to protect it from extinction, it doesn't really work that well, considering that it could be done on Earth. But still, the challenge is fascinating, I think, and I hope a human mission to Mars will one day leave Earth and succeed. One of the interesting questions it could answer would be the presence of traces of life on the planet, even if it is long extinct or asleep. If life appeared at some point on another planet of the solar system, then it would strongly suggest that the conditions that allow the existence of life are not that extraordinary. That would be a powerful argument in favor of the existence of life in multiple locations, multiple places in our galaxy. But a base and a few scientists look absolutely possible, however difficult it is, in a not-so-distant future. Now it is not forbidden to dream, and longer term, the concept that has circulated since the 20th century is the idea of transforming Mars or other planets to make them more similar to Earth and habitable by man and Earth-like life. As you know, this is called terraforming. What is terraforming, and is it just a dream or something that could happen for real? The concept appeared in science fiction in the 1940s. It is not that recent. The first notable scientific article about it was written by an astronomer, Carl Sagan, in 1961. And in this article he proposed a theoretical way of transforming the planet Venus to make it habitable. At the time, it was known that Venus had a very dense atmosphere that created a powerful greenhouse effect, and it kept temperatures at the surface at levels that were unbearable hundreds of degrees. The composition of the atmosphere was roughly known. It had water, nitrogen, and carbon dioxide. So he proposed the idea of seeding this atmosphere with algae. It is so dense that algae would have stayed in suspension. They wouldn't have fallen to the ground and be incinerated. Algae would have converted the components of the atmosphere into organic compounds by feeding on them, especially carbon dioxide. This would have progressively removed carbon dioxide from the atmosphere and reduced this greenhouse effect until temperatures dropped to more comfortable levels. And the carbon would have remained captive in a blanket of matter that would have fallen to the surface. The oxygen would have risen to make the air breathable. That was clever, but later discoveries showed that it couldn't work because the clouds of Venus are very rich in sulfuric acid that would have destroyed algae. And another problem, even more insurmountable, was that the atmosphere was just too dense. Algae would maybe break carbon dioxide into carbon and oxygen, but oxygen would have stayed high, whereas pure carbon would have fallen down to the surface, be incinerated, and through combustion would have returned to the atmosphere as a gas. Sagan also proposed a terraforming project for Mars in the 1970s, and because it is certainly the planet most similar to Earth in the solar system, the concept of terraforming Mars has stayed around for decades. As we saw earlier, it is not impossible that Mars had an Earth-like environment in its history long ago, with a thicker atmosphere and abundant water, possibly liquid water. If the mechanisms that made this atmosphere change happened, they could maybe be reversed. I told you before about the likely reasons that made Mars lose most of its atmosphere. There is no magnetic field, so solar wind tends to erode the atmosphere by carrying it away. Then there is the lower gravity than Earth. Mars has 60% less gravitational pull at its surface. Something that weighs 100 pounds on Earth weighs 38 pounds on Mars. So people walking on the surface could not make big jumps like astronauts on the moon, but they would definitely feel lighter than on our planet. It also means that the atmosphere is less bound to the planet than in the case of other more massive planets. And finally, the last reason for the loss of this atmosphere is that when there is carbon dioxide in an atmosphere and water is present, it tends to react with rocks at the surface to form carbonates, which are solid salts. So this tends to draw atmosphere off and bind it to the surface. This happens on Earth, but due to volcanic activity that ejects new gases into the atmosphere, there is a kind of balance, and the Earth's atmosphere doesn't get eroded by its absorption into the surface. So between these various effects, Mars' atmosphere was probably, in the past, carried away into space and absorbed by the planet itself. These problems are due to the mass of Mars, the lack of enough volcanic activity and the absence of a planetary magnetic field. These problems cannot go away easily. This is what Mars is. And for these reasons it looks complicated to give it an Earth-like atmosphere. Because even assuming it could be done, technically and financially, this atmosphere would be unstable and would need constant maintenance, constant readjustments to stay in place. It would have to be replaced artificially, as it tends to get thinner without intervention. There are other technical problems. In order to be habitable, this atmosphere would have to be heated. But Mars receives less light than Earth from the Sun because of the distance. The light level is about 60% of Earth only. So if an atmosphere with the same composition and density as Earth was created, with the same greenhouse effect that retains heat, it would still be insufficient to raise the temperature above 0 degrees Celsius, and water would stay frozen instead of becoming liquid. And then, even if all of this could be overcome, the soils are toxic for us. They contain a lot of chlorine, too much to make them proper for agriculture. They would also have to be chemically modified. All of these problems, and there are others, actually have solutions that are theoretically possible and often within our technological reach. But in practice, it clearly looks undoable for the moment at the scale of an entire planet. We just don't have enough energy and the possibility to send the huge equipment necessary to Mars. But let's imagine we tried. What could be the methods employed to terraform Mars? The starting point would have to be to generate a greenhouse effect that is mostly absent at the moment by injecting gases into the atmosphere. These gases would trap solar heat near the surface and help start a process of global heating that could one day make water at the poles and underground melt. They would also increase pressure and make it more bearable for humans. At the moment, the pressure is just 1% of Earth pressure. So a pressurized suit is absolutely necessary. But if this pressure reached just 25 or 30% of Earth, it would already be possible to go out without a suit. Just an oxygen mask would be sufficient. There are compounds with a significant greenhouse effect, like ammonia and hydrocarbons, that are abundant in the solar system and could be imported to Mars. We know where to find them, for example, on the moons of Jupiter. But these compounds are relatively light, and it could be hard, especially at the start, to make them stay around the planet. Another option would be to release gases with very powerful greenhouse effects into the atmosphere, like fluorine compounds. This includes the famous CFCs that became known for attacking the ozone layer on Earth. But they also are very powerful greenhouse gases. In fact, they are thousands of times more powerful than carbon dioxide. Fluorine is present in Mars crust in higher quantity than on Earth, as far as we know. So an idea could be to manufacture these compounds from the materials present in the soil and release them into the atmosphere. Or, alternatively, send rockets with payloads of compressed CFCs. When it comes to warming the planet, a proposed solution would be to use orbital mirrors to redirect more sunlight to the surface. They could also be targeted at the poles and their layer of solid carbon dioxide to try and sublimate it and help kickstart a greenhouse effect. Another necessity would be to oxygenate this atmosphere if it gets dense and hot enough. Science fiction often uses the idea of seeding the planet with algae or vegetation in general. This could help, but this is not such a good solution because the net production of oxygen by terrestrial plants is quite small, even on Earth. Plants reabsorb oxygen at night. And in fact, on Earth, more than 2/3 of oxygen is generated by the oceans. Liquid water would be probably necessary to fill the atmosphere with oxygen, and vegetal life that can initially resist extreme conditions of low pressure and cold would have to be introduced. Or an alternative solution would be to create oxygen from water in industrial plants. As you know, oxygen is the main component of water with hydrogen. And finally, if all of this can be sorted out, there will always be the problem of Mars' inability to retain its atmosphere. So as a solution, the idea of creating an artificial magnetic field was proposed, which in theory could be achieved with superconducting rings built around the planet in which electric current would constantly circulate. At the scale of a planet, this is of course very theoretical. So as you see, the terraforming of Mars is not for tomorrow, or even the day after tomorrow. But at the end of the day, technical solutions are not completely out of reach. It could become a viable project in the future if mankind had considerable sources of cheap energy at its disposal, way more than today. But with equipment that could harvest the sun's energy or generate it through fusion, it is not completely unthinkable in several generations. Before we leave Mars, I told you we would visit a volcano. Mars may be smaller than Earth, but it is home to one of the largest and tallest mountains known in the solar system, Olympus Mons. Olympus Mons is an enormous shield volcano. That is to say, a volcano that has grown a very wide base made of the lava it has ejected along its history. Olympus Mons has a surface as big as Italy or Great Britain, and its peak reaches 26 kilometers high, or 16 miles. That's more than twice Mount Everest. It is believed that such a large volcano could appear because of the lack of plate tectonics on Mars. On Earth, a lot of the energy and pressure under the crust is released in rifts between plates, and volcanoes are not eternal. They are parts of plates that move and at some point may disappear in the very, very long term. But when this mechanism doesn't exist, a volcano can stay in place and keep releasing lava for hundreds of millions of years. This is probably why and how Olympus Mons could reach such a size. And this is interesting because if lava keeps nearing the surface on Mars, and assuming there are pockets of water trapped underground, then in some particular locations there may be liquid water under the surface, water heated by geothermy. There are so many other interesting things to say about Mars. It also has satellites, and we are at an exciting moment historically when it comes to space exploration. After the initial exploits of going to the moon and sending probes to the various corners of the solar system in the 1960s, space exploration had slowed down in the following decades. But there is a resurgence happening at the moment with different actors. There is NASA, private companies, China, the ESA, Russia, Japan. Many of the missions and projects planned are collaborative. Maybe not with China, but in general they are. It still may seem painfully slow when you follow space news on a daily basis. These projects take years. But on a historical scale, it seems we are returning to the kind of excitement there used to be in the 1950s and the 1960s, and I'm happy about it. As you know, Jupiter is the largest planet in the solar system, and it is visible to the naked eye on many nights. The first planets from the Sun in our system are rocky: Mercury, Venus, Earth, and Mars. Beyond the orbit of Mars begins the realm of gas and ice giants, planets that do not have a well-defined hard surface, but are giant balls of gas, denser and denser as you approach their core. And it is believed that underneath all these layers of increasingly hot gases, they have a solid core where metal dominates. These include Jupiter, Saturn, Uranus, and Neptune. But rocky bodies can still be found beyond Mars, and there are many of them. Some float in a region called the asteroid belt between the orbits of Mars and Jupiter, including fairly large ones like Ceres or Vesta that are not large enough to be classified as planets, but they follow their own orbit around the Sun. And beyond Neptune, there is also an even larger asteroid belt, the Kuiper belt, that includes Pluto or Eris. And in between these two asteroid belts, in the region of the gas and ice giants, there are many, many rocky and solid bodies of all sizes that have been captured and turned into satellites by these gas giants. Jupiter has dozens of satellites. Some are called moons because they are larger, and due to their size they tend to adopt a ball spherical shape. Others are smaller asteroids, sometimes a few miles across or less, all the way down to small rocks and dust. Saturn has so many small objects in its orbit, and they are so brilliant that they form visible rings. Jupiter also has rings, but they are less large and less dense, which is why they are more discreet. A longer cruise we will land on several of the larger satellites, including the four main ones that are called the Galilean moons of Jupiter, because they were observed for the first time with a rudimentary telescope by Italian astronomer Galileo in the 17th century. But first, let's go to Jupiter. In our last cruise to Mars, I told you about the distance and how an itinerary could be decided based on orbits and the distance from Earth to Mars. Because the distances between planets are constantly changing depending on their own movement along their orbits. Sometimes they can be aligned on the same side of the Sun, in which case they are closer, or they can be on either side of the Sun, and in that case the distance is much more. The same applies to travel from Earth to Jupiter. When the two planets are at their closest point, the distance is 365 million miles, almost 600 million kilometers. At its farthest, it is almost twice as much. Now, to get a sense of distances inside the solar system, let's bear in mind that Earth is actually much closer to the Sun than it is to Jupiter. The distance between Earth and the Sun is about 93 million miles. And to express astronomical distances in a simpler way, an unit, the astronomical unit, was defined. One astronomical unit is equivalent to the distance between our planet and the Sun. So, by definition, Earth is one astronomical unit away from the star, and Jupiter is 5 times farther, precisely 5.2 astronomical units, meaning that the planet and its moons receive less solar energy, and also that light from the Sun reaches them later than Earth. The sunlight needs only 8 minutes to reach Earth, but it needs 43 minutes to reach Jupiter. Being farther from our star, Jupiter also has a much longer orbit than Earth, and it is slower on its orbit. Actually, the farther planets are from the Sun, the slower they tend to be on their orbit. This is an effect of gravitation. The fastest planet in the solar system is also the closest to the Sun, Mercury, and it travels in space at almost 50 kilometers per second. That's equivalent to more than 100,000 miles per hour. Earth travels at close to 30 kilometers per second. Jupiter is significantly slower, only 13 kilometers per second. And so, between the longer distance to close one revolution around the Sun, plus the slower speed, Jupiter needs a lot more time to complete a full revolution and orbital journey around the Sun. It needs about 12 of our years. The one characteristic that makes Jupiter stand out in the solar system is obviously its large size. It is still a very small body compared with the Sun, less than 1,000th of the Sun mass, but it is much bigger than any other planet, and even bigger than all the other planets of the solar system combined. Its mass is 2.5 times the mass of all the other planets together. will pay more attention to Jupiter later, including its composition and formation history. But for now, we are approaching its periphery, and it is time to take a look at its bigger moons. As I told you, there are 4 of them: Io, Europa, Ganymede, and Callisto. They are all very different from one another, and we're going to make a stop on each one. These 4 moons are called Galilean moons, as we said earlier, because they were first observed 4 centuries ago by Galileo Galilei. At the time, they were the first objects found to orbit a planet other than the Earth, and their discovery was a big deal because it challenged views on the nature and the shape of the cosmos. I will also give you a link in the description to my story about cosmology and the evolution of descriptions of the universe over time. Jupiter was always well known since the dawn of human times, because it is visible in the night sky. After the Sun and Venus, it is the 3rd brightest object. But its satellites are way too small to be visible to the naked eye. So only the use of a rudimentary telescope made the observation possible. We will see their history, their orbits, and how these orbits are in resonance with each other. But for now, let's approach the first one, Io. Io is the closest to Jupiter of the 4, the innermost, and the 3rd largest of Galilean moons. It is slightly larger than our moon, and it is a very dense body, the densest of any moon in the solar system. It also stands out for its volcanic activity, which is extreme. There are more than 400 active volcanoes at its surface, and some of them produce plumes of sulfur that climb as high as 300 miles, that's about 500 kilometers. This makes the surface of Io constantly ravaged by eruptions and clouds of gas released by the volcanoes. To us, it may look almost like a representation of hell. So why is Io so geologically active? Because of the presence of Jupiter and other moons, but especially the mass of Jupiter. It causes a phenomenon called tidal heating. What is it? You know that rocky planets and moons in the solar system are very hot inside. Their crust at the surface solidified because it became cooler over time, and with this cooling process over millions and millions of years, the crust tends to become thicker. But there is still intense heat inside that remains trapped as a consequence of mainly 2 phenomena. First, there is the creation of these bodies when a lot of smaller asteroids and dust collided to form them. These collisions generated a lot of energy, a lot of heat, that dissipates very slowly because it is accumulated inside, under the crust. And then there is a second and more important phenomenon that happens inside planets: radioactive decay. Unstable large atoms like uranium and a few others fission. They suddenly reorganize their particles into smaller atoms, and in the process process, they liberate energy and free particles that do not get stuck into the new atoms. This fission of unstable atoms tends to make them disappear over time, but it takes hundreds of million years for some of them, and there are less and less, but they still maintain a residual presence. Their decay, this radioactive decay, because it liberates radiation, is a natural phenomenon, and it keeps hitting rocky planets from within, or satellites. This radioactive decay also happens inside the Moon, our Moon, and there is most probably the same mechanism inside Io. But in the case of this body, a much bigger contributor to its internal heating is the mass of Jupiter nearby and the gravitation forces that result from it. As Jupiter is very massive, the side of Io that is closer to the planet has a slightly larger gravitational pull than the opposite side. And due to the presence of other moons around Jupiter that influence its orbit, the orbit of Io is not perfectly circular. It is elliptical. Depending on its position, the Moon can be closer or farther from Jupiter. This means that as the Moon is in motion, it is subject to different intensities of gravitational pull, and this force causes distortion of Io's shape, as if you had an orange in your hand and you would squeeze it, press it in different parts. It is not going to destroy it, but it is going to flex its interior. This happens to Io, and at the scale of a rocky body like this one, it means constant friction inside the planet, which generates heat. And this is tidal heating, the gravitational pull of a large body that is strong enough to distort its satellite, as the satellite follows an elliptical orbit and moves from being closer to being farther constantly. More than any moon in the solar system, this hits the inside of Io due to friction, and this is what drives its intense volcanic activity. There is a lot of energy waiting to be released, and the constant flexing of the Moon makes its surface prone to moving and breaking. Apart from volcanoes, more than 100 mountains have been identified that have been uplifted by compression of the crust. Io may be way smaller than Earth, it is about the size of the Moon, but because of that, it has mountains higher than Mount Everest. And in between these spectacular mountains, there are rocky plains, and here again, volcanism influences the Moon. Because lava is constantly released, Io has a relatively young surface that gets renewed with new material coming from the inside of the Moon. On telescopes and cameras, Io appears in shades of yellow, white, black, red, even green, that correspond to different types of sulfur. All the surfaces on moons and planets tend to have visible craters, the remains of asteroid impacts, but Io doesn't, because the surface flows of lava that can sometimes be several hundred miles long, they constantly renew its surface and erase traces of impact. There is a very tenuous atmosphere on the Moon, First, because it is not massive enough to retain a thick atmosphere, and second, because Jupiter is close, as we said, and tends to steal gases from Io due to its gravitational pull. It is estimated that the atmosphere loses a ton of matter per second due to this. This is not that much on such a scale, and the faint atmosphere gets renewed by gases released by the volcanoes, mainly sulfur dioxide. As soon as they are released by the volcanoes, these gases tend to freeze due to the intense cold. The inside may be very hot, but Io is much further from the sun than we are. There is no atmosphere to retain heat, and when the moon passes in the shadow of Jupiter, it does not receive any solar energy at all. But when Io is exposed to the sun, a superficial layer of this sulfur dioxide sublimates, which means that it returns instantly to gaseous state, and this is what maintains a bit of atmosphere. There would be much more to say about Io, but let's change setting and move to a second moon, one that also has exciting features, Europa. Europa presents a few cracks and streaks on its surface, but it has the smoothest surface of any known solid body in the solar system. There are very few craters or mountains. It is the smallest of the 4 Galilean moons, and it is slightly smaller than the Earth moon. Why the smooth surface, and what is Europa made of? Its density suggests that overall its composition is similar to terrestrial planets of the solar system. Primarily, it is made of silicate rocks, that is to say, large quantities of silicon and oxygen, and it is likely that its core is rich in metal, especially iron. But the smooth surface and other observations strongly suggest that the outer layer of the moon is made of water. This layer would be about 60 miles thick, 100 kilometers, and so the surface of Europa would be essentially frozen water ice. And the question is, if temperatures are higher under this layer of ice, there could be an ocean of liquid water underneath. But first, what is the dynamic of this solid surface? Because it features a lot of darker streaks of lines that are visible from space. The most likely explanation is that there were, and there continues to be, eruptions of ice between plates. The ice under could be warmer and erupt, causing the crust to spread open and expose warmer layers beneath. In a sense, this is a phenomenon that reminds of oceanic ridges on Earth between plates, even though in this case the environment and material involved are completely different. So, this is compatible with the existence of a subsurface ocean. If the ice under the crust is warmer, there may be a point where the temperature is high enough for water to become liquid. What would heat this ocean? High temperature from the inner layers of the moon, and here again, like for Io, this phenomenon of tidal heating that we just discussed. It may contribute to warm up water. Surface temperatures are extremely cold, At the equator, we are talking about minus 160 degrees Celsius. That's minus 260 degrees Fahrenheit. Again, because there is barely any atmosphere, and Europa receives less sunlight than Earth. At the poles, the temperature plunges to minus 220 degrees Celsius. And it also passes in the shadow of Jupiter regularly for several of our hours. Europa takes 3.5 days to complete a revolution around Jupiter, so for several hours in a row it is plunged in complete darkness and no longer receives direct sunlight. At this moment, the surface temperature at the poles must drop to levels that are not that far from the absolute zero. So in any case, the ice crust is thick, at least several miles or several kilometers, but there is an ongoing debate about how thick it is, and this is important because if it is thin, relatively thin, there could be exchanges between the liquid ocean and the surface from time to time, when these streaks form, or maybe when an asteroid hits the moon and breaks the crust. Whereas if the ice crust is dozens of kilometers thick, the hypothetical liquid ocean and the surface would be totally separated. But in any case, the existence of liquid water is likely on Europa, and that could possibly be a lot of water if the water layer is about 100 kilometers thick, which is the dominant theory at the moment, and even if half of it is solid ice, that would make more liquid water than on Earth. This is absolutely huge. So if there exists a place with water and heat coming from the inner layers of the moon, then this raises the possibility of the existence of life on Europa. And this is why this moon has had a high profile among the moons of Jupiter in the past decades, since various discoveries were made. Discoveries about Europa itself, its composition, and discoveries on Earth, in the abyss. We know that life is possible in complete darkness, with food chains that start with bacteria able to resist very high pressure and temperature. Bacteria that can feed on chemicals released by the Earth's crust. And then bigger and more complex organisms that feed on these bacteria. So maybe a similar phenomenon exists dozens of kilometers under the extremely cold ice crust of Europa, in the darkness and high pressure of its subsurface ocean. This is just about theoretical conditions for life that could be present on the moon. There was never any proof that it exists, but there are long-term projects for missions that could go to Europa to search for evidence of life. Now, even though life exists somewhere on Europa, it doesn't mean its surface would be welcoming to human beings at all. Apart from the cold, radiation is very intense due to the lack of atmosphere and the lack of magnetic field like the one we have on Earth. And Jupiter, which is close, emits heavy radiation. So any manned mission would have to leave behind very heavy anti-radiation walls or buried deep down in ice under the surface to find protection against this radiation. Europa is the smallest of the 4 Galilean moons, as I said. Now let's go to the largest and the third one outward from Jupiter, which also has yet again a completely different environment, Ganymede. I told you that Europa needed 3.5 days to orbit Jupiter. Ganymede needs 7 days. And actually there is an interesting interaction between these three satellites, Io, Europa, and Ganymede, and the planet Jupiter. The three satellites are in orbital resonance. Their orbital periods are synchronized. Europa needs exactly twice as much time as Io to orbit Jupiter, and Ganymede twice as much time as Europa. So that is exactly 4 times as much time as Io. They are in an orbital resonance of 1, 2, 4. What is this concept of orbital resonance, and why does it happen like this? As you know, all planets in the solar system orbit around the Sun, which has by far the biggest mass of any object in the system. Actually, the Sun represents more than 99% of the matter in the entire system. But the Sun is not the only body that influences orbits. Even though they are smaller, planets also have an influence over each other. That depends on their masses and the distances between them. So it is true to say that the Sun determines orbits, because it is by far the biggest factor. But if we go a bit further into detail, it is not 100% accurate. Other bodies, every body, also has a small influence on every other one. A large planet can distort the orbit of a smaller body and eventually modify it so much, revolution after revolution, that this object may be placed on another orbit or even expelled from the solar system. This probably happened many times along the history of the solar system, and there is a phenomenon that can greatly increase the influence between two bodies in space. It is when they exert regular, periodic influence on each other. For a comparison, think about when you are pushing a child on a swing. The swing has its own frequency, but even without touching the ground, the child can amplify the movement by pushing with his body, because this pushing acts in a periodic repetition, and it has a cumulative effect on the motion. On a bigger scale, this is what can happen between planets, or the moons orbiting a planet. And this is this phenomenon which is called orbital resonance. Very often this mutual influence is unstable. The two bodies exchange momentum, and it shifts their orbits progressively to the point that the resonance disappears. But under some circumstances, sometimes, a resonant system like this can become stable because it is self-correcting. The exchange of momentum between bodies keeps them in a stable resonance. It is the case, for example, between Neptune and Pluto. The two are in a resonance of 2, 3. It means that when Neptune does precisely 3 revolutions around the Sun, Pluto does exactly 2. And the same kind of resonance formed between Io, Europa, and Ganymede in a ratio of 1 to 4. When Ganymede does 1 revolution around Jupiter, Europa does 2, and Io does 4. Another effect of momentum and gravitation that applies to Ganymede is that the Moon is also tidally locked to Jupiter. This means that it always presents the same face to the planet. Most moons have this characteristic. They don't rotate on themselves. It's the same with our moon. We always see the same face, looking at it from the Earth. But now let's take a look at Ganymede itself. What Ganymede stands out for the most is that it is the largest moon in the solar system. Its diameter is only 40% the diameter of Earth, but it is bigger than the planet Mercury. It is not as massive as Mercury though, because Ganymede is made of lighter material, lighter elements. Mercury contains a lot of metal, whereas it is estimated that Ganymede has a core of metal and rock, but is also half made of water, in different states, different types of ice. I'll come back to this. And maybe between them there could be liquid water. So as for Europa, there is speculation about the possibility of life in the oceans of Ganymede, but it looks less likely or harder to prove for several reasons. First, because the outer layer of ice is much thicker than on Europa, so reaching the liquid part looks very hard, close to impossible at the moment. And also it is uncertain whether the bottom of this subsurface ocean reaches the rocky mantle underneath. It is believed that there is another layer of ice, but not the same type that we are familiar with. On Earth, we essentially know ordinary water ice, frozen water, which forms at certain conditions of pressure and temperature, typically when the temperature drops below 0 degrees Celsius and at sea level pressure on Earth. But if the pressure is higher, you need a lower temperature for water to freeze. Now you know that ice is a crystalline form. It means that water requires a highly ordered microscopic structure. Billions and billions of molecules become perfectly ordered, following a pattern. It almost never happens on Earth because of the conditions of temperature and pressure we have on our planet. But there are different possible crystalline forms, different patterns that water may adopt. And these different crystalline structures could be explored and studied in laboratories, showing that different types of ice may exist. Ordinary water ice is called Ice 1, and many other possibilities of structure have been identified, Ice 2, 3, 4, 5, and so on. It is believed that the inner layer of ice on Ganymede is Ice 3, which forms when liquid water is exposed to a temperature of -20 to -30 degrees Celsius, plus a pressure of 200 to 300 times the sea level pressure we have on Earth. On our planet, these conditions can only exist in a laboratory, because naturally, where there is enough pressure, at the bottom of oceans, the temperature is higher than that. And where the temperature is low enough, because -20 to -30 degrees Celsius is perfectly reachable in the winter in many parts of the world. But in that case there is not enough pressure because it is at the surface. So these conditions are not naturally met in our environment, but it seems they are in the depth of Ganymede's oceans. So at its surface, Ganymede is mainly made of water ice, but there are other elements that probably arrived as a result of impacts with smaller bodies. 1/3 of the surface is dark and covered in clays and organic compounds that are believed to be traces of impactors that collided with the Moon. Contrary to Europa and Io, the surface is quite ancient in average, because there is not much activity that renews it, but there are still grooves and ridges that are not completely explained at this point, given the structure of the Moon, but that could have appeared maybe hundreds of millions of years ago, when its surface was more active than it is now. Ganymede may have less chance of harboring life than Europa, but when it comes to human presence and exploration, it may be a bit more welcoming. There is less radiation because of the longer distance to Jupiter, and also thanks to a degree of protection from a magnetic field that seems to be generated, like on Earth, by the dynamo effect of a rotating metallic core at the center of the Moon. The level of radiation is still deadly, and the temperature and pressure very hostile, but with adapted protections it is not impossible to think of a human base one day on Ganymede. Out of the different moons of Jupiter, Ganymede presents a less difficult set of conditions than Io and Europa. But there is even better. Callisto. We still have a fourth Galilean moon to look at. Callisto is the fourth of them by distance to Jupiter, and thanks to this, it has the lowest radiation levels, but there are other interesting features that distinguish it. I told you that the surfaces of Io and Europa were fairly young in astronomical times, that is to say, still millions of years. But in contrast, Callisto has the oldest solid surface in the entire solar system. It seems that since its formation, there was never any kind of subsurfaces processes like volcanism or plate tectonics that could have rejuvenated the surface. So it never changes at all, except for impacts. Callisto has the most cratered surface in the solar system. It is completely covered in impact craters that have appeared over probably several billion years. So why is Callisto so inactive geologically? It is believed that this is due to its formation history. Callisto would have formed very slowly from the accretion of smaller rocks, but not fast enough to reach a high temperature inside. And as a result, the Moon is not fully differentiated internally. What it means is that bodies of a certain size, planets or large moons, tend to have a structure in layers internally. The heavier elements converge to the center, to the core, and various elements above it form layers that are clearly distinct in terms of chemical composition and conditions of temperature and pressure. It is the case of rocky planets like ours and the 3 first moons we just visited. This process of differentiation is never at 100%. For example, there can be movements in the mantle of a planet that can make small quantities of metals go up and reach the surface. But still, large bodies acquire an organized structure overall, one that is differentiated. But this process was very incomplete on Callisto, and it makes it the largest body in the solar system that is not fully differentiated. Elements inside are mixed up, and there are several layers made of rock and ice mixed together. Here again, the various conditions mean that the structure of ice differs depending on how deep it is inside the Moon. The crust is made of ice 1, the ordinary one on Earth, but inside it is believed there is also ice 5, 6 and 7 with different crystalline structures. And under tens of miles of icy crust, probably yet again another ocean of liquid water that has been isolated from space for billions of years, since nothing ever happens on the surface of Callisto except occasional impacts that do not reach beyond the icy crust. After the Earth, Moon and Mars, Callisto is a possible target for manned missions one day. Clearly not in the 2020s or 30s. It is way farther than Mars, and there is no specific project now. But if one day men set foot on one of the moons of Jupiter, it is likely to be Callisto first. The low radiation level and the geologic stability are advantages, and Callisto could be a good base as a station for further exploration of the solar system and remote exploration of Europa in the search for traces of life, for example. Until now, we have spoken about the 4 main moons of Jupiter, but there are many more of smaller sizes that were discovered long after. You remember that Galileo observed these 4 moons in 1610. It took almost 3 centuries then, to the end of the 19th century, to start discovering more and smaller moons of Jupiter. Today, at this point, 79 moons in total have been found and named. They are called moons when they are large enough, and there are also moonlets and dozens of smaller satellites. Together with the planet, they form a system called the Jovian system. We'll take a look at some of these smaller bodies and also at the rings of Jupiter. But before, let's talk about the planet itself. As you know, Jupiter is by far the largest and the most massive planet of the system. It has 2.5 times the mass of all other planets combined. It is also probably the oldest planet of the system, the first to form, according to current models of planetary formation. These are all theories based on our knowledge of the history of the solar system and physics, not absolute certainties. But the dominant models, right now, suggest that Jupiter formed quite far from the Sun, beyond the limit called the snow line. This is the distance to an early star where it is sufficiently cold for volatile compounds like water to condense into solids. The origins of Jupiter would have started with a large, solid core, one of rock and metal, that would still exist today at the center of the planet, and around which huge quantities of gas like hydrogen and helium would have aggregated, kept together by gravitation. After a few million years, which is short at this scale, The various other planets of the solar system were not formed yet, and the system was essentially a gigantic disk of gas and dust, with a newborn star in its center. So rather quickly, Jupiter gained enough mass to absorb or satellize everything on its orbit to clean it up, and reach a mass that was already 50 times the Earth's mass. Nowadays, after absorbing more gases and rocky bodies, Jupiter is more than 300 times as massive as Earth. But because it is less dense, being primarily made of gas, it has 1300 times the volume of Earth. Now, the fact that it is a gas planet doesn't mean that it is like a cloud that could be crossed easily. The more you move towards the center, towards the core, the denser and hotter the planet becomes. Due to the mass, temperatures and pressure inside Jupiter reach levels that are way higher than at the center of Earth. And the gravitational forces that keep the planet together are very powerful. Jupiter has a composition dominated by hydrogen. It is about 3/4 of its mass and 90% of its volume, and it is so much matter that the interior is strongly compressed. This compression generates heat, and actually Jupiter emits more heat by itself than it receives from the Sun. But however massive Jupiter is, it is not enough to ignite the same reactions of fusion between atoms of hydrogen that happen inside the Sun, which is why it didn't turn into a star. We know that there are systems where more than one star forms, even though this is not the most frequent case. If Jupiter had gained more mass, it could have turned into a second star after the Sun, but the planet stayed well short of that. It is estimated that it would need to be 75 times more massive to ignite fusion. So because it is a gas planet, there is no solid surface to land on. The planet begins as a cloud of low density and becomes increasingly dense. If we were to enter this big ball after gaseous hydrogen, we would reach a layer of liquid hydrogen turned into liquid by the rising pressure, followed by another layer of so-called metallic hydrogen. Another phase of hydrogen. It doesn't mean it turns to metal in the usual sense of the term, but that under such conditions, hydrogen behaves like an electrical conductor, which is why it is called metallic hydrogen. Jupiter and also Saturn would contain a lot of this metallic hydrogen form due to their large masses that compress hydrogen. Now visually, when we look at Jupiter, we also see several bands or belts of color, different colors, that are segregated all around the planet. And there is also a giant spot. These bands move at different speeds. They are made of clouds of ammonia that float in the upper layers of the atmosphere, and their movements cause strong turbulences. In its upper layers, Jupiter has powerful winds. The various bands have different circulation patterns, they move at different speeds, and their interactions create turbulence and even storms. This is what the Great Red Spot is believed to be. It is a vortex, a storm, that probably did not always exist, but became a stable feature of Jupiter's atmosphere. Jupiter being very big for a planet, the red spot is bigger than Earth, and it rotates counterclockwise, in the opposite direction to the bands of clouds. The phase of fast growth is long over for Jupiter. There is no longer much matter to aggregate, like in the early stages of the solar system. But the planet keeps attracting bodies, like comets, that are captured by its gravitational pull and fall on it. Jupiter would receive about 200 times more asteroids and comet impacts than Earth. For a long time, it was believed that Jupiter played an important role here in shielding rocky planets, including ours, from asteroid impacts, because it would have acted as a gravity well located at the limit of the inner solar system, being the first and biggest of giant planets. So Jupiter would have been like a vacuum cleaner of the system. But this view is now more disputed, because also due to its mass, Jupiter could attract more asteroids and comets to draw them from the Kuiper belt, the larger belt of asteroids that exists beyond Neptune. So this debate is still open, and it is unsure at this point whether Jupiter is such a shield for Earth. But in any case, due to its mass and age, Jupiter has the largest number of large satellites of any planet in our system, and it also has rings. These rings are not obvious like the rings of Saturn, and actually they were discovered only recently, in 1979, when a space probe, Voyager 1, explored the Jovian system. These rings are not as large comparatively as Saturn's, and they are way less bright, which is why they were not seen before. Saturn's rings contain a lot of ice that reflects light, whereas Jupiter's rings are primarily made of dust. And in between, or around these rings, there are more moons, dozens of moons. I told you earlier that Jupiter had 79 in total, so let's explore a few of them. Other Jovian moons than the four largest ones started to be discovered in 1892, and they are much smaller, so they were harder to identify from Earth. Initially they were given numbers, Jupiter 5, 6, 7, and so on. Jupiter 5 is also called Amalthea, and it is the fifth biggest moon, and the last one discovered by direct visual observation. The following ones were found by photographic or digital imaging, that is to say they were seen on photographs of space using extended exposure time, which allows to capture objects that could not have been noticed otherwise. Like other smaller moons, Amalthea interacts with Jupiter's rings. These rings contain dust ejected from the surface of these moons. Amalthea is also not large enough to acquire a spherical shape, so it looks irregular. Its maximal length is about 160 miles or 250 kilometers. Put near Earth, it would look about the size of Massachusetts or Belgium. It is believed that this moon formed far from Jupiter, because its structure is light and it contains water ice. In the early stages of Jupiter's formation, the planet emitted a lot of heat, and based on the distance to Jupiter, it is very close, this moon would have entirely melted. So the theory is that Amalthea formed farther in the solar system and was captured as a satellite afterwards. Visually, the moon looks very red, which may be due to sulfur it will have collected from Io, which is also close, but this is uncertain. Amalthea orbits at only 180,000 kilometers from Jupiter, which is only a bit more than the diameter of the planet. It looks really close. So if we were to land on this moon and look at Jupiter, the planet would look huge. Imagine something 8 times bigger than the moon when we watch it in the night sky. But there is even closer than Amalthea. Jupiter 16, also known as Metis, is the innermost known moon of Jupiter. It orbits at only 130,000 kilometers, which is less than Jupiter's diameter. And it is the fastest moving moon of all. It orbits at 30 kilometers or almost 20 miles per second. This moon is far too small to be spherical. Its maximal length is 60 kilometers by a width of 40, so it looks like a big asteroid. And Metis is just in the middle of one of the rings, and this is not a coincidence. It is dust from this moon that generates the ring. When there are impacts with rocks, material can easily be ejected from Metis because of the low gravity. And there are 2 more moons like Amalthea and Metis, Adrastea and Thebe, that also have irregular shapes. And then there are 70 more smaller moons that orbit much farther from Jupiter. It is believed that these bodies had their own orbit around the Sun, like asteroids from the asteroid belt, and they were progressively captured by Jupiter. They float in space away from the rings and are only a few miles across sometimes. Some of them follow a prograde orbit, that is to say, they orbit in the same direction as Jupiter's rotation, and others are retrograde, which is the opposite. These ones travel the opposite way of Jupiter's rotation. It is well possible that more will be discovered. At this point, more than 20 of these small, irregular satellites have not been named. They were just given a number. And discoveries continue. As recently as 2020, more candidates were found on orbits that are far from the planet, and the population of moonlets could be in the hundreds. It depends where the limit size is fixed. First of all, what distance do we need to travel to go to Saturn? As I told you when we visited other planets before, the answer is always, it depends. It depends where Earth and Saturn are on their respective orbits. If they are opposed on either side of the Sun, this distance is going to be bigger than if they are aligned on the same side of the Sun. When they are at their closest distance, so on the same side of the Sun, the distance between them is about 1.2 billion kilometers. That's 750 million miles, or about 7 astronomical units. An astronomical unit is the distance from Earth to the Sun, and it is a convenient unit to compare distances in the solar system. So that gives you an idea of how far Saturn is from the Sun in comparison with our planet. By definition, we are 1 astronomical unit away from the Sun, but Saturn is almost 10 times farther, at 9.5 astronomical units, give or take, because orbits are not perfect circles. They are slightly elliptical, oval-shaped, so the distance to the Sun varies a little over time, depending on which position the planets occupy on their orbit. In other terms, our planet, seen from Saturn, would look really close to the Sun. And this is why when Saturn is on the other side of the star, opposite to us, the distance increases, but not dramatically. It increases to 11 astronomical units instead of 7 at its shortest. If we were to travel at light speed, it would take us around 1 hour to get to Saturn. Luckily, we are traveling by the mind, so this is going to be even shorter than that. And on our way, we will cross the orbits of Mars and then Jupiter before arrival. So, as we are now leaving the Earth's orbit and beginning to accelerate, let's talk a little bit about what we will find when we reach Saturn. As you probably know, Saturn is called a gas giant, and it is the second largest planet of the solar system after Jupiter, another gas giant. Gas planets do not have a solid surface, like rocky planets. They are made of layers of gas, increasingly dense, and it is believed that at their centers there is a solid, rocky or metallic core, around which the gas accumulated during their formation process. Gas planets are kept together by gravitation. The large mass around the center of these planets pulls the gas and keeps the planet as one single body. It is believed that gas planets have to be of a certain size. They cannot be small like the size of Earth or Mars, because it takes a certain mass for them to stay in one piece. But an hypothesis is that gas and rocky planets may have similar origins. They start with a solid body, a core that appears in the formation process of a star system, in orbit around a star. These planetoids grow by absorbing smaller objects in and around their orbits over millions and millions of years. And they can also grow, sometimes, by absorbing asteroids that travel across the star system. This is how Earth and other rocky planets, Mars, Venus, Mercury, are thought to have formed. But on the orbits of Jupiter and Saturn, that are significantly farther from the Sun than these rocky planets, there could have been on top of that a lot of hydrogen, and to a lesser extent helium, that had not been absorbed by the Sun. This is the matter they would have attracted. And these floating gases, collected by the two planets that completely cleaned up their orbit, would have become the various layers of these gas giants. I am using the conditional here because even though there is a broad consensus about the main lines of the formation history of the solar system, there are also variations between models, and these models, these theories, are inherently hard to prove. It is not as if we could recreate the experience. For example, if you look at the solar system in isolation, it seems to suggest that rocky planets would tend to be located near the star, It is the case for the 4 rocky planets of the solar system: Mercury, Venus, Earth, and Mars. And further away, you would find gas giants like Jupiter and Saturn, and even farther, ice giants like Uranus and Neptune. But the observation of other star systems and the growing number of exoplanets discovered, this also indicates that other placements of planets are possible. For example, gas giants that are located near their stars. These planets are called hot Jupiters because they are close to a star. Maybe they formed away from their star and they changed orbit later, so it does not necessarily disprove the theory that gas giants appear far from stars. But this is to illustrate that debates about the formation history of star systems and the appearance of the different kinds of planets are still open. We will elaborate much more on Saturn itself, but for now we have considerably reduced the distance with the planet, and it is becoming bigger and bigger. We have passed the orbit of Jupiter, which was about halfway in our journey. The size of Saturn, and its even larger rings, is becoming very imposing. The planet is actually almost as large as Jupiter, even though it is not as massive, and by a margin. It has 3 times less matter, 3 times less mass than Jupiter, meaning that it is less dense, and we will see later why it can be almost as big with less than a third of Jupiter's mass. But before we reach the planet itself and its rings, let's spend some time exploring its moons that are not less interesting. The moons of Saturn could be a topic by itself, because they may not be as famous as its rings. But Saturn has more moons with confirmed orbits than any other planet in the solar system. In total, 146 moons. But this number raises the question of what we define as a moon. Technically, each block or even each particle in the rings of Saturn is a satellite of the planet, and there are billions and billions of these particles in the rings. These are way too small and not independent enough to be called moons. The moons I am referring to are not part of the rings. They are distinct bodies, and they have been accounted for among the 146 moons I mentioned only when they could be repeatedly observed and their orbit identified. If we lowered the bar of what a moon is and accepted smaller bodies, there could be hundreds more. But tonight we're going to pay a visit to some of the biggest. Titan, which is the largest moon of Saturn and a very big moon, the second biggest in the solar system. Rhea, the second biggest. Iapetus, the third, and also Enceladus. Each of them have different things to reveal. So let's begin by taking a look at Titan, the largest and most famous of these moons of Saturn. It is actually so big for a moon that only one is larger in the solar system, Ganymede, the moon of Jupiter. For comparison, the diameter of Titan is 40% of the diameter of Earth. So Titan is significantly smaller than our planet, but it is about 50% wider than our moon. For reference, our moon is number 5 by diameter in the solar system. Number 1 and 2 are Ganymede and Titan, as I said, and number 3 and 4 are two other moons of Jupiter, Callisto and Io. Number 6, just after Earth's moon, is yet another Jovian moon. Jovian means of Jupiter, Europa. Another element of comparison is that if Titan was not a satellite of Saturn, but had its own independent orbit around the Sun, it would be considered as another rocky planet, because it is larger than Mercury. Larger, but not as massive. Titan only has 40% of the mass of Mercury. Mercury is mostly made of iron and dense rock, whereas a large portion of Titan is made of ice that is way less dense than these materials. Despite the distance with Earth, Titan was discovered relatively early, by the mid-17th century, by a Dutch astronomer, Christian Huygens. It is quite far in comparison with the moons of Jupiter that had been discovered a few decades earlier by Galileo, about twice as far. But Titan is big for a moon and relatively shiny, with an uniform yellowish atmosphere. This helped Huygens detect and study it. A bit like the planet Venus, Titan reflects sunlight and is far enough from Saturn to be distinguished from it with relatively rudimentary telescopes. But then, for 350 years, our knowledge of Titan remained very basic, because like for Venus, its surface was impossible to see, hidden under a thick and opaque atmosphere. A lot of what is known about this moon's surface and atmosphere was discovered in the past few decades by probes, and in particular in 2004 when a probe, Cassini, approached it. It is rather uncommon for a moon to have a thick atmosphere. It can only happen when moons are large enough for their gravitation to retain this atmosphere. But we have seen that Titan was the second biggest moon of the solar system. And also, over hundreds of millions or even billions of years, they have to retain this atmosphere, because an atmosphere can be lost due to a collision with another body, or by passing too close to a planet that could steal it, or it can be carried away by solar wind, which is the flow of particles and radiations that comes out of the sun. So the conditions are drastic, and probably for this reason, only two moons with a significant atmosphere are known in the system. There is Titan, and the other one is Triton, a moon of Neptune. The two moons are relatively big, and they are far from the planet they orbit, and also far from the Sun. Different conditions that probably explain why they have been able to retain their atmosphere. Now, other moons generally have a very faint atmosphere. It is not dense enough to be comparable to the kind of atmospheric conditions we are familiar with on Earth. Titan is really different, because its atmosphere is very heavy and dense. so dense actually that surface pressure is higher than the one we have on Earth. It is estimated to be close to 1.5 atmosphere. That is to say, a slightly higher, 50% higher level than the one we are accustomed to at sea level on Earth. Something that would be perfectly bearable to human beings. The sensation of pressure would be like swimming a few feet underwater. Now, the atmospheric pressure may be livable, but the other conditions are not. The composition of the atmosphere is mainly nitrogen, at 97% of it, plus methane and traces of hydrogen. Our own atmosphere is 70% nitrogen, but we also have 20% of oxygen that we can breathe. There is no gas oxygen on Titan's surface, and so we couldn't breathe without a suit. Another major problem for human beings would be the temperature. Titan is almost 10 times as far from the Sun as Earth, and this means it only receives about 1% of the sunlight we receive. So, not much sunlight, and on top of that, 90% of it is absorbed by the thick atmosphere. Only the remaining 10% reaches the surface. Now, because the atmosphere is thick, there is also a greenhouse effect like on Earth, and this helps retain a bit of heat. But all in all, the temperature is still very cold, about 94 Kelvin, or negative 179 degrees Celsius, a temperature at which water would freeze instantly, but it would be even colder without this greenhouse effect. And yet another problem that man would have at the surface would be the constant darkness. With 1% of sunlight and a thick atmosphere hiding the sun, you are plunged almost in constant night. But let's say we have a suit with heating, an oxygen mask and lighting. What would we see at the surface of Titan? An extraordinary landscape, actually. At the same time, completely alien, chemically, but somewhat familiar by its geography. Titan is thought to have standing bodies of liquid on its surface, including rivers, lakes, and seas. Except these bodies don't contain water, because it would freeze, but liquid hydrocarbons, like methane or ethane. Titan is believed to be the only place in the solar system, except Earth, to have such liquid bodies, with a cycle of evaporation, clouds, and rain, like on Earth, except it is not water, but hydrocarbons. Apart from this cycle of precipitations, mountains and volcanoes have been observed, but not Earth-like volcanoes. These are cryovolcanoes. A cryovolcano erupts volatile materials and gases, such as ammonia, water, or hydrocarbons, all these materials that astronomers call ices. It is not just water ice. It is believed that these materials ejected by cryovolcanoes come from reservoirs under the surface, a bit like lava on Earth, but these are much colder materials and they are not rock. It has also been observed that the surface of Titan looked relatively young, because it doesn't have many impact craters. For a part, this may be thanks to its atmosphere. Like ours, a dense atmosphere eliminates small asteroids by destroying them. But it is also because there is a geological activity on Titan. It seems new material is expelled from the inside of the Moon, supposedly by these cryovolcanoes, in large enough quantities to replace surface material slowly, on a scale of several million years. But this eliminates traces of impact and refreshes the surface. One last question about Titan that was raised when this set of conditions and composition became better known is about the possibility of organic life on this moon. At the surface, this sounds very unlikely due to the temperature. But like for other moons of the solar system, like Europa, the moon of Jupiter, there could be subsurface oceans under the thick ice sheet. And in these oceans, maybe, the bricks for simple organisms, prebiotic conditions, could be present. There is no proof at all today that Titan harbors any kind of life. And if it does, it would have to be life that relies on other energy sources than sunlight, like the life forms on Earth that depend on hydrothermal vents near the ocean floors. They depend on them for the energy and nutrients that they need. But this is theoretically possible. In a weird way, Titan is considered the body in the solar system that looks the most like Earth geographically. But obviously the materials and the climate are very different. And the surface of the Moon is constantly plunged in the dark. At this distance, even if the Sun could be seen through the atmosphere from the surface, it would only be a very distant and faint light in the sky. Not the big shiny ball we are accustomed to. Now let's take a look at the second biggest moon of Saturn, Rhea. Rhea is much closer to our idea of a moon. It is made of rock and ice. It barely has any atmosphere, only a very tenuous layer of gas. And it is significantly smaller than our moon. It was discovered 20 years after Titan by an Italian astronomer, Cassini. Hence the name of this mission to explore the moons of Saturn, Cassini-Huygens. These were the early discoverers of Saturn's moons. Rhea may not be as remarkable or as original as Titan, but it holds one record. It is the smallest body in the solar system which has been precisely measured to experience hydrostatic equilibrium. What does it mean? Planets are round, and moons too, down to a certain size, whereas smaller bodies can be irregular. But there is no example of a body the size of Earth, for example, that would be elongated or irregular. This happens because above a certain mass and density, objects in space adopt this spherical shape. But why is that? Because of hydrostatic equilibrium, which is a concept from fluid mechanics. And it is simple to understand. The material inside planets or moons, under their solid crust, is viscous, fluid. It consists of very hot material, rock and metal generally. What makes this material stay together, is gravitation. As you know, the reciprocal attraction of all this matter keeps it as one single object. And gravitation pushes on the material that is at the center of the body. The outward layers of matter above have a weight that compresses the center of the ball. If this gravitational force was left unchecked, the body should collapse on itself. The mass would stay the same, obviously, but it would become smaller and smaller because the matter would be more and more compact. It doesn't happen because there is an opposite force, the one that pushes materials to expand. This, in physics terms, is called the pressure gradient force. So gravitation and the pressure gradient are opposite forces in that case. And the volume of a body stabilizes at the point where the two forces cancel each other. Large objects in space tend to become spherical because of the equilibrium of these forces. The spherical shape is the one that spreads forces evenly around the center. But this happens only on large-scale objects that are not entirely solid. A small or medium-sized asteroid is not affected by this because it is not viscous and it is not big enough for gravitation forces to compress it and for its core to melt. But planets and some moons are subject to this equilibrium, and this is why they are round. The pressure gradient force and the equilibrium it forms with gravitation are also important for the Earth's atmosphere. If there was no resistance to gravitation, the entire atmosphere could be pulled to the ground and could not be dozens of miles thick as it is. And if there was no gravitation, the Earth's atmosphere would expand around the planet and diffuse into outer space. It would get lost. Our atmosphere is as it is and stays in place because there is this hydrostatic equilibrium at play. And sometimes it can work in ways that are a bit counterintuitive. You remember earlier I told you that Saturn was almost as big, as voluminous as Jupiter, and yet it only had a third of its mass. How is that possible? This happens because the mass and the size of a body are not systematically moving in the same direction. It would sound logical that if you take a planet and give it more material, the planet is going to turn bigger. But in fact, no, it doesn't work like this. The planet will become more massive if you give it more matter. It will contain more matter. But this is also going to affect its hydrostatic equilibrium. And it could actually diminish its size instead of increasing it, due to the increase in the gravitational force. So Rhea is remarkable in that sense because it is the smallest known body in the solar system that is subject to this hydrostatic equilibrium, and as a result it gained its round shape. If it had just been a touch less massive, Rhea would have had an irregular shape. Now let's take a look at another moon, also discovered by Cassini, Iapetus. Iapetus is named after a titan of Greek mythology, like various moons of Saturn. And this moon is close to Rhea by size, and its composition is also estimated to be close: ice, and to a lesser extent rock. At first sight, Iapetus may look spherical, but it is not. It is just below the hydrostatic equilibrium line. And this gives it unique features in the solar system. The poles are squashed, and at the equator there is a very long and high ridge, a mountain chain, giving Iapetus the appearance of a walnut. This mountain chain is impressive, especially considering the size of this moon. The mountains are up to 20 kilometers high. For comparison, that is more than twice Mount Everest. On a moon that is much smaller than Earth, Iapetus would have about the surface area of Australia, for comparison. It is unclear how this ridge could form. And there are several hypotheses about it. It could have been created by the collapse of a ring system, or by icy material from inside the moon that would have been ejected. Or maybe it is a remnant of its formation, because based on observed impact craters, the ridge looks very ancient, almost as old as the moon itself. Another mystery about Iapetus is its coloration. One hemisphere is dark and the other very bright. The difference is really obvious, and the reasons for this have puzzled astronomers since the moon was observed from closer. Here again there are theories. One of them, which sounds possible, is that Iapetus receives infalling material on one of its sides from another smaller moon of Jupiter, Phoebe, and this would be the explanation for the marked difference in color. Before we go on our journey, let's have a look at one last moon with yet another unique feature: Enceladus. Enceladus is small, not large enough to be spherical, and it has an ellipsoid shape. That is to say, the shape of a sphere compressed on both sides. If you put a ball in a press and press to flatten it, you get an ellipsoid. Its small size made it harder to see from Earth, and it was discovered only in 1789 by a German astronomer, Herschel, more than a century after Titan and Rhea. But Enceladus is one of the most reflective bodies of the solar system. It reflects light because its surface is covered in ice. Ice that stays fresh and clean, because on a large part of its surface, this ice is renewed by frequent cryo-eruptions coming out of these cryovolcanoes that we mentioned earlier. Enceladus is thought to have subsurface liquid oceans, and it is yet another moon that is thought to possibly have a set of conditions favorable to biological life. Again, not surface life like on Earth, but life in the depths of dark oceans under the icy crust. How do we know or estimate what these distant moons are made of, by the way? Some of them have been approached by probes, but we never went there or take samples after all. These estimates are obtained by different methods. A first one is to cross the size and the mass of celestial bodies. The size can be observed, and the mass can be deduced from their influence on other bodies due to gravitation. These calculations are complex and they involve multiple bodies and unknowns, but astronomers and mathematicians have worked on these celestial mechanics issues for literally centuries. If you have an estimate of the size and the mass, this may give you a first idea of what a body can be made of. For example, if it is very massive, very heavy for its size, this points to heavy materials like metal, whereas if it is light, it could be ices or lighter rocks. Then there is a second set of information that comes from spectroscopy. What is it exactly? Different elements have different signatures. They emit on different electromagnetic wavelengths. And we can measure these wavelengths. So, analyzed with instruments that can measure and interpret where they are on the electromagnetic spectrum, distant bodies can reveal a lot of information about what they are made of. Here again, this is no golden bullet because the signals are faint, especially for distant bodies. The signals get mixed, so they need to be analyzed to build hypotheses. But this is another valuable source of information. And yet another method is to recoup all this with what we know of the chemical composition in their environment and the formation models. We know, for example, that heavier elements tend to migrate towards the core of a planet, whereas lighter elements will stay closer to the surface. We know that a certain set of conditions, of pressure, of temperature, puts elements in a given state, solid, liquid, gas, or other states. I'll say a word about metallic hydrogen when we dive under the surface of Saturn. So, with these sources of data and the interpretation that we can do with them from the various disciplines that astronomy touches on, physics, chemistry, mathematics, optics, spectroscopy, we can build solid hypotheses about what planets and moons are made of, and how they are structured internally, even without having physically traveled there. Still, these are only theories and not certainties. Maybe there will be changes in the future. There were some in the past. But at this point, they are the best informed guesses we can make based on available information. As we continue to approach Saturn, it is now time to talk about its rings. The 4 moons we quickly looked at are farther away from the planet. But as you know, because you have seen pictures of Saturn, the rings start quite far from the planet too. They are gigantic. And actually they are even bigger than pictures suggest, because what we see on photos or artist views is just the most visible, the densest or shiniest part of the rings. In reality, they extend on tens of thousands of miles, more than the planet's radius. These rings are also incredibly thin relative to their size. Their thickness varies from 1,000 yards, which is less than a kilometer at most, to only 30 feet, 10 meters locally. This is not even the proportions of a sheet of paper. The rings are incredibly thin. But we see them so well, or at least the rings that are relatively close to the planet, because they are also very shiny. They are made almost exclusively of water ice, with a bit of dust, but barely, less than 0.1%. The main rings are made of billions and billions of particles and small objects. The largest ones are only a few meters or yards across. And they are all little satellites that turn around the planet together. This ice is clean enough to reflect sunlight. And this is why we see the rings so well. Another fact that could sound counterintuitive is how little water or little matter the rings contain. The total mass of the rings has been estimated, and it is less than the Antarctic ice sheet on Earth. So, for comparison, we have to imagine that the ice sheet of the South Pole from Earth would be spread on a surface, an area, that is 80 times larger than the total surface of Earth. That's how thin and delicate these rings are. But why are they so big, and how and when did they appear? Historically, the dominant hypothesis was that the rings dated from the formation of the planet or close, and so that they were very old, billions of years old. This hypothesis was not based on very solid measurements or models, and it was increasingly challenged, especially a few years ago when the Cassini spaceship explored the rings. They were revealed to be much less massive than thought. And it was also confirmed that they regularly lost some of their matter, that fell down to Saturn. This means that this type of rings comes with an expiration date. They will get depleted eventually. A problem for the old rings theory is how shiny they are. Over time, they should have collected cosmic dust, particles that would have darkened them. But as I said, they are made of 99.9% pure water ice. So, from these observations, it appeared that the rings could be much younger, maybe, only 10 to 100 million years, which would be a small portion of Saturn's existence. And based on current observed depletion rates, the rings may disappear in 300 million years. The age of the rings is something, but it doesn't tell us how they would have formed. And here there are two main theories. An old one is that the rings are left over from the original nebular material from which Saturn and the whole solar system formed. All these particles would have turned into satellites of Saturn early in its formation process, and so the planet would always or almost always have had these rings. As we said before, this theory is now rather old-fashioned, because it fails to explain why the rings would be pure ice, and it doesn't take depletion of the rings into account, because this was not known when this theory appeared. The second theory, which under different variants is now dominant, is that the matter the rings are made of comes from an old moon of Saturn. The orbit of this moon would have decayed, that is to say, the moon tended to fall toward its planet instead of maintaining the same distance to it. And once it was close enough, the attraction from Saturn's big mass, the tidal forces as they are called, would have ripped apart this moon. It would have been shattered over time into all these small pieces that stayed in orbit and formed the rings. A variation of this theory is that it were not tidal forces but a collision between this moon and a comet or a large asteroid that shattered it. This would check with the relatively small quantity of matter in the rings. You remember, they contain less material than the Earth's southern ice sheet. But this theory doesn't fit really well the composition of the rings, almost pure ice, because there is no example of a pure ice moon anywhere in the solar system. There are floating blocks of water ice, yes, and water is abundant on many moons. But the moons with the most water, like Enceladus that we visited before, still have about 20% of rock. So, if that happened, if a moon was ripped apart near Saturn, why did its ice stay in orbit and its rock disappeared? Hence another variant of the same origin theory for the rings. It would not be an entire small moon, but just the ice mantle of a larger moon, maybe a moon the size of Titan. Such a moon would have decayed, its orbit would have decayed during the formation period of Saturn, and its mantle of ice would have been stripped and stayed in orbit, whereas the rest of the moon would have fallen into Saturn and have been absorbed by it. But these are all theories with their own merits, and nothing is sure. For example, the brightness of the rings, their purity, is cited as proof that the rings are young and not hundreds of millions of years old. But maybe the darker material could have stayed in certain areas of the rings. They are not uniform. There are divisions between them and zones that appear more or less bright. Maybe clumps form within the rings with impurities, and then they would be disrupted by impacts which would automatically clean up the rings. We don't know for sure. But at this point, the best hypothesis for the presence of all this matter in orbit around the planet remains a shattered moon, entirely or partially. What we really don't know is when and how this happened. You saw pictures of the rings, so you also know that they have like stripes, subdivisions, lines that are more or less bright, and in between them, sometimes entirely dark spaces. Different subdivisions have been established based on their appearance and the distance to Saturn. A common one starts from ring D, the closest to Saturn, which is quite faint and was confirmed only in 1979 by a probe Pioneer 11. Then there are rings C, B, A, with divisions between them, and after that it turns a bit confusing if you keep moving away from the planet, because the ring after A is called F, and after that E. These different divisions have different physical characteristics, like their thickness and the density of particles that makes them more or less bright. But let's keep approaching. We are now right in front of the imposing mass of Saturn. I told you at the beginning it looked almost as big as Jupiter, even though it has less than a third of Jupiter's mass. And this has to do with this equilibrium of mass and size that we discussed before. Being more massive, Jupiter is more compressed, so it is also significantly denser than Saturn. In terms of chemical composition and structure, if we leave aside this difference of density, the two planets look alike. They both are gas giants, thought to have a metallic and rocky core, around which enormous layers of gas have accumulated and stay stuck together by gravitation. Now we say gas because its main components are hydrogen and helium, and in that the planet reflects the composition of the nebular cloud from which the solar system formed. It was thought to be mainly hydrogen, followed by helium, the two simplest elements, and the rest, the other elements, were present in very small quantities proportionally. But don't imagine that Saturn is just like a cloud. It is way denser than that. Around the core, it is believed there is a layer of metallic hydrogen. That is to say, hydrogen that is so compressed that it goes beyond liquid. It is in a state called metallic because it can conduct electricity. I told you about it already in the space cruise to Jupiter and its moons, or when we detailed the table of elements. Above the layer of metallic hydrogen, there is liquid hydrogen and liquid helium, and only above that begins a truly gaseous outer layer. So there are parts of Saturn that are denser than anything on Earth, and in total, the planet has 95 times the mass of Earth. For comparison, Jupiter has more than 300 times the mass of Earth. But if you take an average, with these outer layers of gas that are little dense, Saturn has an average density that is lower than water, about 30% less dense than water. So, still in average, it could be called a relatively light planet. It is not pure hydrogen and helium, too. As we said, the core is thought to be metallic and rocky, and there are traces of other elements. This is where the yellowish hue of the planet comes from. In its upper atmosphere, there are crystals of ammonia that give it its color in natural light. Apart from that, the planet has less features than Jupiter. Its surface is rather uniform, with just a bit more yellow around the equator. And it doesn't show on pictures, but its shape is not really that of a sphere. This is due to its rotation and its relatively low density. The rotation creates a centrifugal force, and this flattens the planet a little bit. It becomes an ellipsoid, like Enceladus, the moon we visited before. Except, contrary to Enceladus, Saturn is not a body with a solid surface. It is a rotational ellipsoid. It takes this ellipsoid shape due to its rotation. If the rotation stopped, which is not going to happen, but let's say it would, theoretically, then the centrifugal force would dissipate and the planet would become a sphere due to this hydrostatic equilibrium that we talked about before, that would no longer be altered by the rotation. Like for other gas planets, if we approach Saturn and start diving into it, there is no precise surface, just an increasing density of gas around us, that after hundreds of miles of travel towards the core of the planet becomes so dense that it turns into liquid, then metallic, and after that there is a molten core of heavy material, metal, probably predominantly iron, and rock, silicates. Being that much farther from the Sun than Earth, it takes more time to Saturn to complete a revolution, a Saturnian year, almost 30 of our years. During this long revolution, the aspect of Saturn seen from Earth changes a little. We see it under different angles, at times from above the rings, and the rest of the time from under the rings. This is so because all orbits of planets around the Sun are on the same plane, but this plane is not perfectly uniform for each of them, each of these orbits. The orbit of Saturn is slightly elliptical, and compared with the orbital plane of Earth, it is slightly inclined by a bit more than 2 degrees. So, if we take the orbital plane of Earth as a reference, Saturn crosses it twice in 30 years, when it passes above and then below. And this is why the planet is seen half of the time, and for several consecutive years, from above, and then from below, slightly. Its surface may look peaceful and quiet in comparison with Jupiter, which has stripes of color, moving, and a red spot which is thought to be a gigantic storm. But this is misleading. In its upper atmosphere, Saturn has some of the most violent winds of the solar system, at 500 meters per second for the fastest ones observed. These are only second to the winds of Neptune, when it comes to speed. Again, for comparison, the speed of sound in our atmosphere is 360 meters per second. And here, at 500 meters per second, these winds are supersonic. At its southern pole, Saturn also has an unique feature, a warm polar vortex, that is to say a region of rotating gas, in that case a big one because it is the size of Earth, around which blow the fastest winds observed on the planet. Heat, supposedly coming from inside Saturn, is ejected from that vortex. The average heat in the atmosphere of Saturn has been measured at minus 185 degrees Celsius, but the temperature measured in that vortex would be about 60 degrees warmer, at minus 122 degrees Celsius. It is still freezing cold there, but less so, and these temperature differences probably explain and influence the violent winds around the vortex. There could be many more things to say about Saturn, Some people dedicated their lives to the study of this planet. How far are Uranus and Neptune from us on Earth? You remember from our previous space stories that there is an unit that is useful to figure out distances in space, the astronomical unit. It was defined, roughly, as the equivalent of the distance from the Sun to the Earth, which is about 150 million kilometers, 93 million miles. Light takes about 8 minutes to travel this distance, and the astronomical unit is convenient to compare distances between the orbits of planets. So, the Sun to Earth distance is 1 astronomical unit, the Sun to Mars 1.5 units, Jupiter, which is the 5th planet from the Sun, is at a bit more than 5 astronomical units. Saturn, the 6th planet, is almost twice as far as Jupiter, 9.5 astronomical units. But to reach Uranus, we need to double that distance again, about 19 astronomical units. 19 is like a middle point, because the orbit is not a perfect circle, it is slightly elliptical. At its closest, the distance is a bit more than 18 astronomical units, and at its farthest, a bit more than 20. But a good order of magnitude to bear in mind is that Uranus is 19 times farther from the Sun than Earth, and Neptune is 30 times farther. At this distance, light and heat from the Sun take more time to reach them, and there is much less. They don't have a solid, rocky surface, as you know, so we cannot really say that they have a cold surface. But the upper layers of these planets are extraordinarily cold. We will see how cold when we approach them. The first close images we got from Uranus are not very old. They were taken by a probe, Voyager 2, in 1986, and they revealed a planet that looks almost featureless, without the kind of cloud bands and storms that are observed on other giant gas planets. Neptune looks more animated, but both planets have conditions in their upper layers that are some of the most extreme in the solar system. So first, let's talk about what they are made of and why they are called ice giants. Until the 1940s, astronomers distinguished 2 main types of planets in the solar system: the rocky ones, with a solid surface, like Mercury, Venus, Earth and Mars, and gas planets, which are bigger and do not have a clearly defined surface, because they are made of gas in various layers, denser and denser as you move towards the center. And their core is believed to be made of rock and metal, around which gas has accumulated and stays, kept together by gravitation. There were 4 gas planets: Jupiter, Saturn, Uranus and Neptune. It was assumed that their composition was more or less similar, mainly hydrogen and helium, the two most abundant elements in the solar system, and most probably in the universe in general. They are the simplest, the smallest types of atoms. There are heavier elements, dozens of them, including some that are also relatively abundant, like oxygen, iron, and carbon. But it is believed that these elements are mostly younger than hydrogen. Like other heavier atoms, they would tend to form in stars when they approach the end of their lives. You know that the fuel of stars is hydrogen. Inside them, hydrogen is exposed to such extreme conditions that fusion happens. Atom cores combine to form heavier atoms, mainly helium, for most of a star's life. But when the end of a star nears, because it has consumed a large part of its hydrogen reserves, which takes hundreds of millions of years, billions of years in the case of a star like the Sun, the star starts consuming helium, and heavier and heavier elements are formed. It is believed that this is how these heavy elements appear, all the way to big atoms with dozens of particles, like gold or uranium. And then, when a star dies, it becomes gigantic, it explodes in a supernova, which would disperse these elements, and they would become available to form new systems. Our system is much younger than the estimated age of the universe. I told you about all that in the video about cosmology. I put the link in the description. So if these theories about the universe, stars, and the formation of star systems are accurate, it is not surprising that these heavier atoms are actually present in our solar system, either alone or combined with others, in compounds like ammonia, carbon dioxide, sulfur dioxide, or water. But still, most of the solar system, if we take into account the Sun itself and all the planets, is still mostly hydrogen and to a lesser extent helium. And as it happens, these are also the main components of gas planets like Jupiter and Saturn. They probably have rocks and metals in their core, and they have other compounds in small quantities in their various layers. But this isn't much in proportion. So, until about the 1940s, it was assumed that Uranus and Neptune, because they were giant planets with no defined surfaces like Jupiter and Saturn, had a similar composition. To put figures on this, it is estimated that Jupiter and Saturn are more than 90% hydrogen and helium. But it appeared through spectroscopy and estimates of their mass relative to their size, and later measurements sent by probes, that no, Uranus and Neptune were quite different in their composition. Only about 20% of hydrogen and helium by mass, and a lot of compounds like water, hydrocarbons, and ammonia. These different compounds are called ices in astrophysics and planetary science, because when they are independent from a larger body, like a planet, and at a sufficient distance from a star, they are generally found frozen as solids. On Earth, when we hear the term ice, we think about water ice, whereas in astronomy, ice refers to a broad range of compounds that includes water and various more. These compounds have in common that they freeze above or near 100 kelvins at Earth's surface pressure. They include water, which freezes at 273 Kelvin, which is 0 degrees Celsius. The Kelvin scale is similar to the Celsius scale, except it begins at 0, the lowest possible temperature, whereas the Celsius scale begins at minus 273. So water freezes at 273 Kelvin and 0 degrees Celsius. Ammonia freezes at 195 Kelvin, that's minus 78 degrees Celsius, or methane freezes at 91 Kelvin, minus 182 Celsius. These elements make the majority in mass of Uranus and Neptune. And this is the scientific reason why they are called ice giants. But it can be a bit misleading, because when we hear ice giant, we may think about a planet with a hard surface, which they are not, or one with blocks of ice floating in its atmosphere, which they don't have either. The term ice refers to the compounds they are made of, not the state they are in, because, as we will see, these compounds are no longer solid. They might have been when the planets formed, but they no longer are. The term was needed to differentiate these planets from gas giants, like Jupiter, because their composition and formation history were quite different, and the term ice giant sounded appropriate, which is why it was adopted over the past 40 years. Now, a good question is why some planets are rocky, others are made of hydrogen and helium, and others of ammonia, water, and methane. And why is there an apparent order in the solar system with 4 rocky planets near the center of the system, then 2 gas giants made of hydrogen that happen to be the 2 biggest planets, Jupiter and Saturn, and after them 2 ice giants that are in between rocky planets and gas giants in terms of size and mass. To try answering this, we need to talk about the theories of planet formation. One thing that makes the formation of planets harder to research is that we only have one system at our disposal, ours, and there are not that many planets in it. Only 8 bodies are considered massive enough to be classified as planets, plus a few smaller bodies like Ceres or Pluto, dwarf planets, but that's not many. The starting point of a star system is something relatively uncontroversial among astrophysicists at this point. It is still theoretical, but it is backed by a lot of observations from the chemical composition of planets to their orbits, the laws of gravitation, and even, since 2018, the direct and confirmed observation of a star system in formation around a newly formed star called HL Tauri, 450 light-years away from us. It is far, but not that much at the scale of the galaxy. It is believed that a star system begins to form when enough matter, gas and dust, coming from a nebula concentrates in a smaller space. A nebula is an immense cloud of matter floating in space. There are several in our galaxy. And the main force behind the formation of a star system is gravitation. In this region of space, this matter in suspension tends to take the shape of a large disk that rotates on itself. For this rotation to begin, an initial impulsion is needed. It is believed that supernovas, the final explosions of stars, could provide it, because they send a shock wave in space. As this disk rotates, matter tends to concentrate in the center faster and faster because the mass at the center increases, absorbing more and more matter. And when the mass becomes critical, big enough for pressure at its center to ignite fusion, it becomes a star. Typically, this new star goes through a short period of growth, during which it absorbs most of the disk. In the case of the solar system, more than 99% of it. We know that there are systems with several stars, 2 or even 3, of different sizes. So there is not a single possible accretion model, accretion process, but it seems the single star model, like our system, is the most frequent one. In any case, this doesn't let much matter available, but still enough to form several planets that concentrate the rest of the protoplanetary disk, what the star hasn't swallowed. This protoplanetary or accretion disk is the basis of planetary formation models. But then there are theories that explain differently the specifics of planets' formation, and ice giants are a bit of a problem here, because their existence appeared as a challenge to existing theories when their composition was discovered. The formation of rocky planets like Earth and also gas giants like Jupiter, this is not very controversial. They are widely understood to have formed through millions of years of collisions of smaller rocky bodies within the protoplanetary disk, until one larger planet remains on its orbit, having cleaned up the orbit of all other bodies. But why do some of these planets become gas giants instead of terrestrial planets? It would be because they would have formed bigger solid cores, around 10 times the Earth's mass, and so with a more powerful gravitational pull, they would have also acquired, by accretion, an envelope of gas. Based on the observation that in the solar system, rocky planets are closer to the star, and gas giants farther from it, it is supposed that the distance from the star also helps retain gas. So, for a long time, it was believed that gas giants had to form relatively far from the star, from the center of a system, whereas rocky planets could be more central. Actually, they could theoretically be distributed in a large part of the protoplanetary disk, but they would tend to become satellites, moons, of gas giants if they were close to their orbits. But in the past 2 or 3 decades, this theory, this assumption, has been questioned by many observations made outside our system, with plenty of exoplanets and other star systems. it appeared that there could be large gas planets, exoplanets, orbiting close to their star, and with a very short orbital period. That is to say, they orbit quickly around the star, as little as a few days, to compare with an entire year for Earth or 12 years for Jupiter. When these gas giants that are close to their star were discovered, they were called hot Jupiter, hot because they are close to the star. And clearly their existence raised a challenge to existing theories about gas giants. These are the easiest exoplanets to discover, because they are big and they are close to their stars, which makes them stand out. They are much easier to spot, and there are plenty of hot Jupiters. So the theories were revisited. The prevalent view about hot Jupiters at this point is that they probably form far from their star, and then they migrate closer to it. The migration could be progressive due to an imbalance in the system until they find a stable orbit close to the star, or it could happen due to a collision that suddenly modifies their trajectory in space. An alternate hypothesis is that they form in situ, close to the star, maybe due to a particularly big solid core that has a lot of gravitational pull. The truth is that this remains an open question at this point. But returning to ice giants, the problem they raise is that these models that work well with terrestrial planets or giants like Jupiter have a very hard time explaining the formation of these big planets so far from the star. Why is that? Accretion of a rocky core requires collisions, plenty of them, and the formation of a protoplanet that progressively cleans up its orbit by absorbing everything on it. So at the start, the protoplanets are fairly small, and a theoretical problem here is that given their distance from the star, a protoplanet forming on the orbits of Uranus or Neptune should have been expelled when they were smaller from the solar system. Based on the laws of gravitation, it is logical that a planet like Jupiter or Saturn stays within the system. They are at 5 and 9.5 astronomical units from the star. But the further you are from the Sun, the less you are bound to the system by gravitation. The force decreases with distance, and at 20 astronomical units like Uranus, or even more, 30 like Neptune, with the accelerating effects of Jupiter and Saturn, the protoplanets would have surpassed the escape velocity. That is to say, they would have traveled fast enough in space to overcome the Sun's pull, and they would have left the solar system. Or they should have been pulled and absorbed by Jupiter and Saturn, or turned into comets, before fully forming. But obviously it didn't happen, because they are here. But a planet forming by collision at 20 astronomical units or more from the Sun, and staying there on a stable orbit, is something that formation models have a hard time explaining. And to make things even more complicated, it seems that Uranus and Neptune are no exceptions. Plenty of exoplanets that have been discovered in other systems are candidates to be ice giants. So what could have happened? A first possibility is that they would have migrated after their formation, like possibly hot Jupiters do. They would have started to form somewhere between the orbits of Jupiter and Saturn, 5 to 10 astronomical units from the Sun, and then changed orbit at a time when their sizes and speed were sufficient to keep them bound to the solar system. It is not precisely explained how. There are different theories about this outward migration. It could be, for example, due to close encounters with Jupiter or Saturn that would have expelled them to another orbit. Or another possibility is that they formed differently near their current orbit, but in that case it couldn't be through collisions. An alternative that could work, theoretically, would be that they formed due to instability in parts of the protoplanetary disk. There could have existed regions of slightly higher density in the disk that could lead to the formation of clumps of matter that eventually collapsed due to gravitation to form a planet. Models suggest that a disk with a bit of instability could yield protoplanets between 10 and 30 astronomical units from the star, and both ice giants of the solar system are within this range. So, at this point, the formation of Uranus and Neptune is explainable. The thing we don't know is what mechanism, what process happened, because these processes may have been very different. But we are now at 19 astronomical units from the Sun, approaching Uranus. Even though it is way smaller than Jupiter and Saturn, it was observed from Earth centuries ago, maybe as early as the antiquity. But for a long time it was mistaken for a star or a comet, until the late 18th century, when several astronomers realized that due to its movement it couldn't be a star and had to be a planet beyond Saturn. Uranus is about 19 times farther from the Sun than Earth, as we said, and it is also slower on its orbit, so it takes much more time to complete a revolution, 84 years. Actually, since it was identified as a planet in 1781, it has made less than 3 complete orbits. I also told you earlier that it received much less sunlight than us, due to the distance. The intensity of sunlight varies inversely with the square of distance. In other words, it decreases faster and faster as you move away from the Sun. And so at 19 or 20 astronomical units, depending on where the planet is on its elliptical orbit, it receives 400 times less light than Earth. In other words, Uranus travels in space in the dark, and if we looked at the Sun from it, the Sun would be a small point in the distance, not the big and bright light we see from Earth during daytime. Uranus has several moons, 27 have been identified, and we will explore the biggest of them, Titania. But first, let's start traveling inside the planet, from its atmosphere to its core. What we call atmosphere here is just the envelope of gas, because there is no well-defined solid surface. So the atmosphere has been defined as the region that was accessible to remote sensing up to 100 bar of pressure. That is still hundreds of kilometers or miles within the planet. We saw earlier that the pictures taken by Voyager 2 or telescopes with a lower definition suggest a peaceful, quiet, featureless planet that looks pale blue-green. This is due to the composition of the atmosphere that absorbs red light, but this may be misleading. The planet's atmosphere is very active, and for short periods of time, it happened for 2 months in 2004, for example, large clouds can appear in the atmosphere and spectacular storms can take place. Record-breaking winds have been observed at more than 500 miles per hour, that's more than 800 kilometers per hour. And even though the climate is not very well known, it seems it is subject to big variations. Since the 1990s, and thanks to imaging with higher definition and under different types of light, a lot of clouds and atmospheric phenomena have been discovered. In this atmosphere there is mainly hydrogen and helium. You remember they account for an estimated 20% of the planet's mass, and these elements are thought to be absent from the denser parts of the planet. The third element, that would account for a bit more than 2% of the atmosphere, would be methane, and this aquamarine color of the planet in visible light is probably due to methane. This atmosphere is intensely cold. The temperatures vary depending on the altitude, but in the coldest parts of the troposphere, that is to say the lowest and densest part of the atmosphere, they are near 50 Kelvin, below minus 200 degrees Celsius or below 350 degrees Fahrenheit. I made a story about the Earth atmosphere that explained the variations in temperature, up and down, due to the composition and density of the layers of gas. The atmosphere on Uranus is much lesser known, but it is well established that in the troposphere there are different layers of clouds. Where the pressure is lower, they seem to be made of ammonia, hydrogen and sulfur, whereas where the pressure is higher, they could be water clouds. And these different levels of the troposphere would have a highly complex structure, constantly moving, with strong winds and seasonal variations. Below the troposphere, density and temperature increase. Progressively, hydrogen and helium are less and less present, and we come closer to a kind of mantle made of these ices that give their names to this type of planet. Again, these are not actually solid ices. They probably were before the planet formed, but they are called ices because they are compounds that would be solid if they floated in space, like on a comet, or if they were at the surface of a rocky planet. This mantle represents the bulk of the planet's mass. In total, Uranus' mass is 14.5 times that of Earth. The gas envelope occupies a lot of space because it is not very dense, whereas this mantle is much denser. It represents more than 13 times the Earth's mass and about 90% of the whole planet. Given the conditions, the main components, which are thought to be water and ammonia, are believed to be in a state of dense and hot fluid. This fluid is sometimes called a water-ammonia ocean. By the way, you know what water is, but what is ammonia exactly? When hydrogen forms molecules with oxygen, you get water, as you know. Ammonia is a molecule that hydrogen forms with nitrogen. It is quite abundant in the solar system. There is some on Earth, but it can be found in much higher quantities on Mars, Jupiter, Saturn, and of course Uranus and Neptune, where it is an important component. On Earth, it is found only in trace quantities in nature, and often associated in salts with other elements like chloride or sulfur. But it plays a very important role in the cycle of life on our planet. It is a common waste of the feeding cycle of aquatic organisms, and it contributes to the nutritional needs of terrestrial organisms. Plants need it to grow, and it serves as a precursor to almost half of the world's food. Typically, fertilizers contain some. Now, returning to space, the mixture of water and ammonia has the particularity of freezing at a very low temperature. The melting point is as low as 173 Kelvin, which is minus 100 degrees Celsius, 100 degrees less than water alone. So in space, this water-ammonia mixture could act as an antifreeze and allow the existence of liquid internal oceans at temperatures far lower than it would be possible with water alone. But this is not a concern for Uranus, because where there is this water-ammonia mixture on the planet, the temperature is estimated to be much higher than that. Where the mantle begins, the temperature would be around 47 degrees Celsius, and the pressure 100 bar. That is to say, 100 times the atmospheric pressure at sea level on Earth. And then, traveling deeper into the mantle, temperature and pressure increase, up to extremes at the center of the planet that are estimated to 8 million bars and a temperature of about 5,000 degrees. A hypothesis is that within the mantle, methane, which is also present, could be broken up under the constraints. Methane is hydrogen with carbon, and so pure carbon atoms, could condense into crystals of diamond that would rain through the mantle, almost like stones sinking in a lake, except it is not a lake of water, but of water and ammonia, with very high temperature and pressures that are superior to the deepest abyss on Earth. These rainfalls of diamonds may not be limited to Uranus. Theoretically, they could also happen inside Jupiter, Saturn, or Neptune. Another hypothesis is that at the basis of the mantle, where the core begins, there could be an ocean of liquid carbon. In this state it is called metallic carbon, because it conducts electricity. And yet another curiosity would be the presence of water at such high temperature and pressure that it becomes something called superionic water, or superionic ice. This is the same thing. What does it mean? The conditions are so extreme, and they actually cannot exist in nature on Earth, that the water molecules break apart and oxygen crystallizes. That is to say, it adopts a highly organized and repetitive structure, like a lattice. In between this lattice, hydrogen can float freely. The existence of this state, this phase of water, was only theoretical until it could be synthesized very recently, in 2019. In a laboratory, water was squeezed between two pieces of diamond and maintained at a very high pressure, and then blasted by a pulse of laser. In this experiment, the pressure was 1,000,000 times atmospheric pressure. It defies imagination, but as we saw earlier, pressure inside Uranus could reach up to 8 million atmospheres, so it is theoretically possible in natural conditions on this planet. And the water was heated almost instantly with the laser to several thousand degrees, recreating the conditions that are believed to exist within the mantle of Uranus and Neptune too. As expected, oxygen and hydrogen in water molecules broke apart and oxygen crystallized. This phase of water is also called Ice 18. In a previous story about the moons of Jupiter, I told you about the different types of ice, of water, that are thought to exist depending on the conditions. Ice 18 is one more, and it is likely to exist in a stable state somewhere in the depths of ice giants, even though we are nowhere near the capacity of going there to take samples and check. After the mantle, the last part of the internal structure is the core, around which ices and gases aggregated during the formation process, or possibly where heavier elements migrated. We don't exactly know, as we saw when I told you about the formation history of the planet. This core is thought to be relatively small, around half the mass of Earth, and it would be made of rocks, of silicate, that is to say silicon and oxygen, and also metals. Now that we have quickly seen the inside, let's take a look at the periphery of the planet, because there are more things to see there. First, there are rings. They are not very visible and generally not represented on views of the planet, but 13 of them are known. The majority of them are very narrow, only a few kilometers or a few miles wide, and they are made of very dark particles that vary in size from microscopic to 1 or 2 feet. It is believed that these rings are younger than the planet. It could have been one or several moons that were shattered by impacts and left their matter all around the planet in orbit. Because there is a respectable number of moons around Uranus, we know 27 of them. So let's take a look at the largest one, Titania, which is also the 8th largest moon in the solar system. It is believed to have formed like the other moons of Uranus from a small accretion disk that surrounded the protoplanet in the early stages of the solar system. In its composition, Titania is very similar to several moons of Jupiter that we visited in our last space journey. Rock in the center and an envelope of water. It is unknown whether some of this water could be liquid under a crust of solid ice, but Titania is relatively small, much smaller than the Earth moon. it may not have kept enough internal heat to have underground oceans, subsurface oceans, like Europa or Ganymede are suspected to have. At its surface, there appears to be a lot of canyons. This is not the kind of features that can be created by asteroid impacts. Canyons can appear due to plate tectonics, but Titania is too small for that, or because of erosion. But Titania doesn't really have an atmosphere with meteorological events that could provoke erosion. So a hypothesis is that long ago there was a liquid ocean on Titania under a layer of ice, maybe kept liquid thanks to the presence of ammonia. As we saw before, it is a powerful antifreeze when mixed with water, because it freezes 100 degrees Celsius below water alone. And then, as Titania became colder, as it cooled down, the subsurface ocean would have frozen. This would have made its volume increase, and it would have created these canyons at the surface because it would have broken the hard ice crust. Overall, Titania is an icy desert. It does not produce much internal heat. There is no atmosphere to retain heat, and it doesn't receive much sunlight due to the distance to the sun. But there are still variations of temperature due to seasons, and they are extremely long due to a particularity of Uranus. Uranus has the particularity to present its pole to the Sun, not its equator, like other planets. This could be due to a major collision in the distant past that would have tilted the planet. And the moons orbit around the equator of the planet, and Titania always presents the same face to the planet. It is tidally locked to it. So what it means in terms of seasons is that when Uranus is on one side of the Sun, Titania presents one of its poles to the Sun, and then the other pole. But as Uranus needs 84 years to complete one orbit, this means seasons on Titania last 42 years. One side is lighted for 42 years, whereas the other side is in the dark, and then they switch for another period of 42 years. Now, let's resume our journey and go to our second destination, even farther away from Earth. Uranus is about 20 astronomical units from the Sun. Now we need to travel 10 astronomical units more to reach the orbit of Neptune, which, as we're going to see, is a near twin of Uranus, with a few differences. Neptune is so far away that it is invisible from Earth to the unaided eye, and this is why it was the first planet discovered not by observation, but by mathematical prediction. This happened in the first half of the 19th century. Uranus had been found and was now observed by telescopes, and its orbit was mapped. But something was off. There were unexpected changes in the orbit of Uranus that were not really explainable by the existence of other planets and the laws of gravitation. So either there was something wrong with the calculations, or there was something else, yet another unknown planet that influenced the orbit of Uranus. The position of a possible eighth planet was deduced from the perturbation of Uranus' orbit, and this ghost planet was tracked in the night sky until 1846 when it was found. In the following decades, several moons were also found around Neptune, starting with by far the largest one, Triton. We'll take a look at it a bit later. In terms of composition and structure and size, Uranus and Neptune are thought to be very similar. Envelope of hydrogen and helium, ices inside, that is to say water, ammonia, methane, to a lesser extent carbon dioxide. But in visible light, Neptune looks bluer. This is believed to be due to more methane in the upper layers of the atmosphere, and possibly another component that has not been fully identified. Another difference is that Neptune is a bit more massive than Uranus. It has 17 times the mass of Earth, versus 14.5 times for Uranus. And it sounds counterintuitive, but it is also physically a bit smaller. This is due to its mass. It implies a bit more compression of its atmosphere. And in balance, it is a bit more matter in a bit less space. Another difference is the distance to the Sun. The two planets are 10 astronomical units away from each other, and this is a huge distance, about the same as the distance from the Sun to Saturn. And this means even less sunlight. Neptune is internally a bit hotter because of its bigger mass, so the temperature at the center is estimated at 5,400 Kelvin versus 5,000 for Uranus. But still, its atmosphere is one of the coldest places in the solar system. The temperature approaches 50 Kelvin, that's below 200 degrees Celsius, and only 50 degrees above absolute zero. Since its discovery, Neptune has completed only one orbit around the Sun. It takes 165 years, twice the time Uranus needs. And yet another difference is the intensity of meteorological activity compared with Uranus. Neptune's atmosphere is all but peaceful. There are giant storms constantly, a complex system of clouds, and the most powerful winds of the entire solar system. They blow constantly at more than 1,000 miles per hour in the upper atmosphere. This is believed to be a consequence of the differential in temperature between the core and the mantle, which are hotter than for Uranus, and the atmosphere, which is colder in its upper parts. And as you know, winds are the product of gas masses moving from one place to another, due to a differential in pressure and temperature. And on Neptune, these differentials are bigger. And so the planet looks constantly agitated by giant storms that have been observed since we have higher definition images. For a time there was a big dark spot comparable in nature to the great red spot of Jupiter, and it was a storm. It finally disappeared, but more perturbations are constantly appearing and disappearing at the surface. Beyond Neptune begins a region called the Kuiper belt, a very large region of the outer solar system, with millions and millions of small asteroids. Pluto, the dwarf planet, is one of these bodies. The limits of the Kuiper belt have been set to between 30 astronomical units from the Sun, that is to say Neptune's orbit, and 55 astronomical units. And Neptune has a strong influence on this belt due to its gravitational pull. It has shaped its structure over time after hundreds of millions of years and millions of revolutions around the Sun. An example of that is the number of objects that are in orbital resonance with Neptune in the Kuiper belt. I explained the concept in the story about Jupiter's moons because 3 of them are in orbital resonance. To summarize, it is when 2 or more objects on different orbits become locked by their respective influence on each other, and their revolutions happen in a stable ratio. In the example of Jupiter's moons, every time Ganymede makes 1 orbit, Europa makes 2, and Io makes 4. So they are said to be in a 1-2-4 resonance. Neptune is in resonance with dozens of smaller bodies in the Kuiper belt, starting with Pluto. They are in a resonance of 2-3. That is to say, when Pluto makes 2 revolutions, Neptune makes 3. And there are also other ratios that have been found with other bodies: 3-4, 3-5, 2-5, 4-7. Over time, the Kuiper belt has become strongly influenced by Neptune, by its mass and orbit, in a way that is similar to the influence of Jupiter on the smaller asteroid belt, the one that is between the orbits of Mars and Jupiter. Neptune also has 40 known moons, most of them small, except one, Triton. Triton alone represents more than 99% of all objects orbiting Neptune. All the other moons together are not even 1%. So let's focus on Triton, because it has original elements, original aspects that make it different from most moons. The first one is that its orbit is retrograde. It orbits in the opposite sense to the rotation of Neptune. This is very rare for large moons in the solar system. Most of the time they are the opposite, prograde, meaning they follow the rotation of their planet. This is a strong clue that Triton did not form in the periphery of Neptune, but was captured later, possibly from the Kuiper belt, where it would have been considered a dwarf planet like Pluto if it was still in the belt. Triton is actually a bit larger than Pluto, and almost as large as the Earth's moon. So it is rather big, the 7th largest moon of the solar system. Its surface looks like it was renewed. This can be deducted from the density of impact craters. There are few, and this strongly suggests that if the moon can rejuvenate its surface, it is geologically active. That is to say that it has a differentiated structure with a core, a mantle, and a crust. That would be coherent with its size, and there seems to be 2 kinds of geological phenomena at the surface: cryovolcanism, that is to say, eruptions of warmer materials like water that surge and freeze at the surface, and also tectonic terrain that would release other materials from inside the moon, or that would let plates of crust move. This is how mountains and rifts can appear. How can a body of that size be captured, bearing in mind that distances are huge in the Kuiper belt? There are different possible mechanisms. In any case, it takes a very long time, and maybe millions of orbits around the Sun. Parts of Triton's orbit may have crossed or passed near Neptune's orbit, and bit by bit, the influence of Neptune would have slowed Triton down, so much that Triton's speed could have passed below escape velocity, allowing its capture by gravitation. The slowdown could also have been the consequence of a collision between Triton and an ancient moon of Neptune, now disappeared. Or yet another option is that Triton formed a binary system with another body, like Pluto and its biggest moon, Chiron. The influence of Neptune on this system would have caused the system to interact in such a way that Triton would have been pushed to the orbit of Neptune and its partner expelled from the Kuiper belt, or even possibly from the solar system. We don't know, but it seems the arrival of Triton had catastrophic effects on the ancient moons of Neptune. It perturbated their orbits. There could have been collisions, and small moons could have been dispersed through gravitational interactions. When the system stabilized, Triton represented more than 99% of the mass in orbit around Neptune, the remainder being faint rings and small irregular moons. At its surface, in this region of intense cold, Triton is covered with a layer of frozen nitrogen. There could be an envelope of water, accounting for 15% to a third of the moon's mass, and below that, a mantle and a core of rock and metal. Like for many moons we have visited in our stories, there could be liquid water, a subsurface ocean, that could theoretically harbor life, but this is speculative, and it is already hard to imagine an expedition to Europa or Ganymede, which are 5 astronomical units away from the Sun. Triton is 6 times farther, at 30 astronomical units, so any manned mission to explore it directly is science fiction at this point. It takes a lot of patience to send probes to these regions of the solar system. All space missions take time, but this is really far. You remember we talked about the probe Voyager 2, that was the first to take close pictures of Uranus and Neptune. It was launched by NASA in 1977. It reached Jupiter in 1979, then Saturn in 1981. It took 5 years more, despite an acceleration, to reach Uranus in 1986, and still continuing to accelerate. Neptune was reached in 1989, 12 years after launch. Voyager 2 is still active, by the way, and now on a mission to explore interstellar space, 44 years after departure. The distance it has traveled is absolutely mind-blowing. When it reached Neptune, 32 years ago, it was at 30 astronomical units from the Sun. Then it crossed the entire Kuiper belt, which ends at 55 astronomical units, and it exited the zone of influence of the solar system at 120 astronomical units. That was in 2018. Voyager 1, also conceived to reach interstellar space and launched almost at the same time, is also still operational and is now at more than 150 astronomical units from Earth. These 2 probes are by far the man-made objects that have traveled the farthest ever. A well-known detail about our destination, Pluto, is that it lost its status of planet 20 years ago, in 2006, when the International Astronomical Union, redefined what constitutes a planet. This International Astronomical Union is an independent body that exists to advance astronomy in research or education, and its definitions and policies are relevant because all countries in the world with a research capability in astronomy and space programs participate in it. The US and 70% of countries in North and South America, Europe, Russia, China, Japan, India. So the rules that the International Astronomical Union produces matter and are typically accepted by astronomers and astrophysicians as conventions that facilitate research and cooperation. In 2006, the Union redefined planets, and Pluto was kicked out of the list of planets in the solar system because it no longer met the criteria. What are these criteria? There are three. A planet must orbit the Sun directly. That is to say, a satellite of another planet cannot be a planet, regardless of its size, because it doesn't have its own independent orbit around the Sun. As we will see in our space cruise, Pluto does orbit the Sun, so it qualifies as a planet on this first criteria. Criteria number 2, it must be spherical, or nearly so. This second condition disqualifies objects that are too small, because the ball shape that bodies adopt in space depends on their mass. When they are massive enough, the matter they are made of naturally adopts this shape due to gravitation. Matter gets distributed around a planetary core, generally very dense and hot, due to the pressure of all the matter around it. This transformation into a ball requires a minimal mass, and again, Pluto passes this test successfully. It is big enough to form a ball. Where it fails is criteria number 3. The body must have cleared its orbit of debris. That is to say, it must have attracted and absorbed by collisions or turned into satellites all other significant objects that populated the same orbit. This is not the case of Pluto, nor of another body like Ceres in the asteroid belt of the solar system, this region of the solar system between Mars and Jupiter that has a higher density of small objects. Ceres is the biggest of them. It is spherical. It has its own orbit around the Sun, but it is part of an asteroid belt that it hasn't cleared. So it is a dwarf planet, or a big asteroid too, not a planet in its own right based on that definition. And this is why Pluto lost its planetary status 20 years ago, which mattered because the Astronomical Union makes the rules in that field. But this is just a problem of definitions. In the case of Pluto, this redefinition of what a planet was not random. It reflected a growing knowledge of what was beyond the 8th and now last planet of the system, beyond Neptune. Another immense belt of bodies, called the Kuiper belt, of which Pluto is a part of, together with other bodies we will take a look at. Now we are leaving Earth and heading for Pluto. We will travel at more than light speed tonight. because Pluto is far from us. The distance between Pluto and the Sun is 3.7 billion miles in average, 5.9 billion kilometers. I say in average because the orbit of Pluto is particularly elliptical. It is oval-shaped. At its closest, Pluto is less than 3 billion miles from the Sun, and at its farthest, 4.6 billion miles, 50% farther. Maybe it is more telling to express these distances with light speed. It takes 8 minutes to sunlight to reach the Earth, but for Pluto, it takes in average 5 hours and a half. In other terms, Pluto is 40 times farther from the Sun than we are. So at light speed, it would take us hours to reach Pluto from the Earth. And this is why I said that by the power of imagination, we're going to travel faster than that and cross the orbits of Mars, then Jupiter, Saturn, Uranus, Neptune, and finally reach the Kuiper belt and Pluto, a place from where the Sun is just a bright but small point on the horizon, and barely any heat from it arrives. But if Pluto is small, actually smaller than the Moon, and so far away from us, how was it discovered? It is invisible to the naked eye, like Neptune, which is closer and much bigger. So obviously Pluto is not going to be visible at all without powerful telescopes. The story of Pluto's discovery began in the early 20th century, driven by a quest to find a mysterious body, a mysterious planet X that was believed to affect the orbits of Neptune and Uranus. In the late 19th century, astronomers had noted small discrepancies in the orbits of these two planets. And from there, the hypothesis of another planet appeared, a planet that would cause these discrepancies due to its gravitation. One person that became particularly invested into that search was an American astronomer, Percival Lowell, who was wealthy enough to create his own observatory in Arizona. And from there, starting in 1905, he started scanning the sky, looking for this hypothetical planet X. His intuition, based on flawed calculations, was that this planet would be rather big, 6 to 7 times Earth's mass, and that it would be located beyond Neptune. This second guess turned out to be correct. But despite all his efforts, the mysterious planet X he was looking for did not show up. And Lowell died in 1916 without finding it. But the search continued at Lowell Observatory, and 13 years later, in 1929, a young astronomer called Clyde Tombaugh noted that a faint dot had moved markedly between two photographic plates taken 6 days apart, indicating that it could not be a distant star, but had to be much closer to us. Further observations of this little dot confirmed that it orbited the Sun. Pluto had been spotted, and in 1930, its discovery was announced. A 9th planet of the solar system had been discovered. What puzzled astronomers, though, was that Pluto was much smaller than it should have been, to explain the observed discrepancies in the orbits of Neptune and Uranus. And indeed, there was a mistake there. From the start, the hypothesis of a planet X, based on discrepancies in the orbits of Neptune and Uranus, had itself been based on a mistake. The measurements of Neptune's mass were inaccurate, and so the discrepancies observed were only for a small part due to Pluto's gravitation. The rest was a mistake. Still, despite its small size, Pluto was accepted as the ninth planet and remained unquestioned as a planet for about 60 years. Until the 1990s, because in the 90s, this region of the Kuiper belt, a region of mostly icy bodies beyond Neptune, began to be discovered thanks to improved telescopes. It appeared that Pluto was not really a planet moving alone in space on its orbit, but rather the biggest or one of the biggest objects among many that formed this new faraway asteroid belt called the Kuiper belt. And from there, the status of Pluto as a planet started to be questioned, ending with its reclassification in 2006. But we are now crossing the orbit of Neptune, the eighth planet, which is a bit more than 4 light hours away from the Sun. You remember, Pluto is, in average, 5.5 light hours away. So we are 80% there. And we can now start to decelerate as we enter the Kuiper belt, the world Pluto is a part of. Let's take a look at it. What is the Kuiper belt exactly? And why does it exist? As I said before, the belt is made of small bodies, including dwarf planets. Pluto is the most famous, but we're going to take a look at others too. There are also comets and smaller icy bodies. Now don't imagine something crowded, because it really isn't. The belt spreads on a gigantic space, a kind of donut-shaped space, that begins after Neptune and extends for almost the same distance as the Sun to Neptune distance, about 3 more light hours. So it is a very vast space, and in it there are millions of bodies, mostly small, but their total mass is at most 10% of the Earth mass, a tenth of our planet, maybe less. Spread on such a gigantic expanse, this means that one could cross the Kuiper belt without noticing it. It undeniably exists, but it is very empty, unpopulated. In total, the number of objects of more than 100 kilometers in diameter, more than 60 miles in diameter, is estimated to 100,000, and there are millions of smaller ones. That sounds like a lot, but given the size of the belt, the average distances between them are still mind-boggling. And the vast majority of these isolated objects in the belt, some very small, are what is called icy bodies. Ice, in the astronomical sense, is the name given to different volatile compounds. Volatile, that is to say, a substance that would easily evaporate, turn to gas at room temperature and pressure on Earth. Obviously, in space, the conditions are very different, and they tend to be solid. It can be water ice, but not only. Methane, ammonia, nitrogen, carbon dioxide, these are astronomical ices too, including when they are part of ice giant planets like Uranus and Neptune. These ice giants are not blocks of solid water ice, contrary to what the name may suggest. Ice giants are like a subset of gas giants, like Jupiter or Saturn, except they contain more of these astronomical ices, which makes them significantly different. Which is why Uranus and Neptune, the ice giants, are put in a different category than Jupiter and Saturn, the gas giants. Now these ices, these frozen volatiles, can also be found on much smaller bodies, like the ones that populate the Kuiper belt. And the tail of comets, too, is actually made of these ices. A comet, when it is far away from a star, looks just like any other asteroid. But when it comes close enough to a star, the heat turns the frozen ices into gas, and this is what gives the comet a shiny tail. A tail that cannot be eternal, because every time a comet deploys its tail, it burns or it loses some of its ice component. So it may take millions of years and thousands of orbits, but all comets end up exhausting their ices and losing their tails. In a minute, we will take a look at some remarkable objects of the Kuiper belt. We are going to explore different dwarf planets, Pluto, and also Eris, Haumea, and Makemake. But first, how did the belt form? Why is it there? And what does it tell us about our solar system? The Kuiper belt is widely believed to be a relic of the solar system's formation. And that is particularly interesting, because it means it preserves material from this formation period that has undergone minimal heating or alteration since then, at least compared to bodies in the inner solar system that are closer to the Sun. So in that sense, the belt would be a precious source of information about the early stages and the primordial matter of the solar system. Now there's a scientific consensus about the age of the solar system, about 4.6 billion years, and the main principles of its formation, that is to say from a disk of gas and dust, a solar nebula, from which the Sun and the planets formed. But this consensus ends when it comes to how the Kuiper belt formed, how it appeared. There are different theories. A first theory proposes that Kuiper belt objects formed roughly in situ, where they are today, in the outer solar system, as part of the original material of the solar nebula. I told you about this standard model, this standard theory of the solar system's formation in previous episodes about space. It means that, like for other star systems, ours would be the product of the collapse on itself of a cloud of matter in suspension in space, gas and dust, that would have started to condense and rotate, possibly due to a shock wave in space created by the supernova of a distant star. This is believed to be the trigger to the formation of numerous star systems. So this disk, an accretion disk, because as it would have rotated, its matter would have concentrated at the center, most of its matter, actually more than 99% of it, to form the star. And around it, on different orbits, planets would have ended up absorbing the matter available, clearing their orbits from other bodies or turning them into satellites. The models are more complex than that. They include matter traveling away from the center of the system and at other times coming back with bombardments of asteroids on planets. All these details and their time frame are still debated. But that's the general idea, an accretion disk turning into a star and planets around it. So, according to this first theory, the part of the solar nebula that extended beyond Neptune basically stayed where it was, with accretion turning dust into bigger bodies like dwarf planets, and these many icy bodies, because the low temperature allowed volatiles to condense and form them. And since then, except a few objects like comets that often originate in the Kuiper belt, the belt would have remained broadly unchanged. A piece of evidence that supports this theory is that many Kuiper belt bodies have circular orbits around the Sun, or nearly circular, contrary to Pluto, which has a very elliptical orbit. We will see that later. And this suggests, these circular orbits, that they formed where they are today, and were not significantly disturbed, because elliptical orbits tend to appear after disturbances, when an object is expelled from a previous orbit, or collides with something, or is captured while it already has a high velocity. And it doesn't seem to be the case here for the vast majority of objects in the Kuiper belt, which is why the theory that most of it formed where it is now makes sense. Another piece of evidence is that the elements present in the belt, especially a lot of methane and less water ice than in the inner solar system, this also aligns with models of the solar nebula before the formation of the system. So the elements the Kuiper belt is made of would have already been in the same location billions of years ago. So that sounds like a strong theory, but it has two problems. The first one is that the density of material in the belt is very low, as we've seen before. Actually, so low that it becomes difficult, if not impossible, to explain how dwarf planets like Pluto would have formed there. If the belt had been stable for so long, there would just not have been enough matter density and movement to create these larger bodies. Now maybe most of the belt is ancient indeed, and dwarf planets like Pluto would have arrived later. That's possible. But another problem with the theory that the belt formed where it is, on the outskirts of the solar nebula, is that the belt ends abruptly. After a distance that is equivalent to about the Sun-Neptune distance, the belt disappears. Its density was already low, as we saw, but it drops to almost nothing. Now this is a problem because logically if the belt was born only from a bit of accretion at the periphery of the solar nebula, its density should decrease progressively as one travels away from the Sun, not end abruptly with a clear-cut edge. This again does not completely disprove the first theory, but it suggests at least external influences that this first theory does not account for. So this first theory is not fully satisfactory, but there are other possible explanations for the formation of the belt. The second one is that all planets of the solar system and the bodies of the Kuiper belt formed closer to the Sun, in a range of 10 to 20 astronomical units. 1 astronomical unit is equivalent to the Sun-Earth distance. So 10 to 20 astronomical units is 10 to 20 times this distance. Bearing in mind that today Neptune is at 30 units, and the Kuiper belt begins at 30 units and extends to approximately 50 astronomical units. So, in this other model of the formation of the solar system, called the dynamical scattering model, the 4 giant planets of the solar system, Jupiter, Saturn, Uranus, and Neptune, would have appeared on closer orbits than they now are. And later, gravitational interactions described by this model would have made them migrate outward. Neptune, in particular, would have migrated from 20 to 30 astronomical units, its current position. And as Neptune migrated, it would have scattered plenty of planetesimals and small bodies outward too, creating the Kuiper belt. That sounds like a huge influence for Neptune. But remember that the total mass of the belt is not that big, at most 1/10 of the Earth's mass, so not much in comparison with Neptune alone. This dynamical scattering model has the big advantage of also explaining the resonance of objects like Pluto with Neptune. That is to say that their orbits seem to be synchronized. For example, every time Neptune completes 3 orbits around the Sun, Pluto completes 2. This ratio of 3 to 2 is locked. And other bodies of the Kuiper belt have the same type of resonance with Neptune. So this model describes a much more eventful and chaotic creation of the Kuiper belt. And that's a strength, because it explains some of the dynamics observed in the belt, such as very elliptical orbits, or these orbital resonances with Neptune, that the first theory fails to describe. It would also explain why other planets, like Jupiter, have what is called Trojan asteroids. That is to say, asteroids on the same orbit that remains always at the same distance of the planet, after or before it, on the orbit. This model provides an explanation of the appearance of this phenomenon, as the planets would have migrated away from their original orbits. So that's also a seducing theory. But when it comes to the Kuiper belt, it fails to explain these icy bodies with circular orbits that seem to have appeared where they are now and have been undisturbed for so long. It also leaves questions unanswered about when this planetary migration took place and what caused it. So again, a theory that could bring a partial explanation to the question of how the Kuiper belt formed, but that is not fully satisfactory at this point. And some of the missing points could be in yet other theories that are not so much about the initial formation of the belt, but the possible external perturbations that would have given it its current characteristics. External perturbations could explain the limitations of the first two theories, the presence of elliptical orbits and big bodies despite the formation of the belt in its current location, as in the first theory, or the presence of icy bodies that don't seem to have formed anywhere else for the second one. So, some other theories propose that the Kuiper belt would have been influenced by external events, external factors, such as a close stellar encounter, that is to say, another star passing close enough to the solar system to visibly disturb it, or an undiscovered planet, maybe in or beyond the belt. In particular, I told you that a challenge to theory number one was that the belt ended abruptly, at about 50 astronomical units. The density drops, it ends instead of progressively fading. And that could be due to the passing of a star that would have truncated the belt, attracted everything of importance that was beyond 50 astronomical units, and so created that edge. This is very hard to prove or disprove. It would have happened billions of years ago, and it is possible, but stellar encounters are very rare in our galaxy. Stars typically orbit the galactic center and stay at a distance from each other. So it is likely to remain hypothetical. Another type of perturbation could be caused by a planet, an undiscovered planet, that is sometimes called Planet 9. Planet 9 used to be Pluto, but now that Pluto is no longer a planet, Planet 9 is undiscovered if it exists. This Planet 9 hypothesis was proposed recently, in 2016, based on the observed orbits of objects in the Kuiper belt, orbits that could be influenced by another body, far beyond Neptune. And indeed, the proposed characteristics of Planet 9 place it very, very far, on a highly elliptical orbit that would see its distance to the Sun vary from 400 to 700 astronomical units. For comparison, I told you the Earth is at 1 astronomical unit from the Sun. That's the definition of the unit. And you remember, Neptune is at 30 astronomical units. The Kuiper belt ends at around 50. And now we are talking of a planet orbiting at more than 400 astronomical units. Something like at least 13 times farther than Neptune is from the Sun. This Planet 9 would have 5 to 10 Earth mass and would likely be a gas or ice giant. Given the distance, it would take it 10,000 to 20,000 years to orbit the Sun. The elements of evidence or the clues that support this Planet 9 hypothesis are that several bodies in the Kuiper belt have aligned orbits that could be influenced by a single massive body. Some have orbits that are tilted too, inclined compared with the plane of the solar system. And this also suggests an external influence. Now, to many scientists, that is not enough to prove anything, because the aligned orbits could be due to observational bias. There are tens of thousands of bodies of more than 100 kilometers in diameter in the belt. So statistically, some are going to have comparable orbits. Or the similarities could be due to the gravitational influence of other bodies in the Kuiper belt. So this is still debated. But the existence of a mystery planet 9 cannot be fully ruled out. After all, planet 8, Neptune, was discovered late in the 19th century, and entirely without seeing it. It was discovered due to its gravitational influence. But maybe it was not the last planet of the solar system. If an odd planet exists, so far away that we have not been able to see it yet. Now, let's finally approach Pluto and see what we have. I told you it was smaller than the Moon. Actually, it has about 2/3 of the Moon's diameter. The duration of the Plutonian year, the time to complete one revolution around the Sun, is 248 of our years. The surface was mapped in 2015 by a probe, New Horizons, which revealed the diverse geography. It has icy plains, mountains, craters, and a surface that shows evidence of geological activity, of possibly volcanism or ice flows. Because the surface doesn't look that old. Billion-years-old impact craters have disappeared. And this means surface material must have been renewed somehow. This is one way of estimating the geological activity of planets and satellites in the solar system. The planet's composition includes a mix of ices, rocks, and organic compounds. It is believed the inside consists of a rocky core, a mix of metal and rock, of silicates, that would account for about 2/3 of its mass. Around the core, there would be a mantle of ice, mainly water ice, possibly with a liquid part beneath the surface, an ocean of liquid water or a mix of water and ammonia that could remain liquid because it would be taken between the hot core and the very cold crust of the planet, probably several miles thick of hard ice. The surface is really very cold, and given the distance to the Sun and the absence of a significant atmosphere, the temperature is rather stable around Pluto. In average, the temperature is around minus 380 degrees Fahrenheit, or minus 229 degrees Celsius. That's only about 40 degrees above absolute zero. The Sun is so far away that it doesn't make much difference whether you are near the poles or the equator. But the atmosphere actually changes a bit depending on where Pluto is on its elliptical orbit. When it is at its farthest, temperature falls to minus 400 degrees Fahrenheit. and there would not be any significant atmosphere at all when it happens. But when it is a bit closer to the Sun, the slight rise in temperature to minus 360 degrees Fahrenheit makes some of the ices at the surface sublimate. That is to say, they turn into gas and form a temporary atmosphere that gets quickly lost because the small mass of Pluto does not retain it. So as soon as the temperature decreases again, these volatiles are lost or return to solid state, fall on the surface, and Pluto loses its thin atmosphere again. This cycle would repeat with each revolution of 248 years. I told you there could be an ocean, a subsurface ocean, under the thick ice layer. Like many bodies of the solar system, starting from the asteroid belt and including different satellites, it is believed to maybe have such a dark ocean with a relatively hot floor. The heat from the core in such a planet or dwarf planet comes from two things. There is residual heat that remained trapped there from its formation, because the formation happened with collisions, and there is also radioactive decay. We know that this is a factor that contributes to the heat inside our planet. As you probably also know, it is speculated that on some bodies of the solar system, these subsurface oceans could, maybe, harbor forms of life, maybe rather basic life, but life made possible by a liquid medium, energy, heat from the hot core, and chemicals dissolved in the water. We have no signs at this point that this potential for life has led to the actual appearance of life forms. And other bodies, such as Europe, for example, a satellite of Jupiter, are seen as more likely to harbor it. But it is not completely impossible that in the depths of Pluto's subsurface ocean, if it exists, life chemistry could be at play. Now, what is easier to investigate is the surface. And on the surface we have different kinds of ices. There is nitrogen ice, methane ice, which is found across the surface, water ice, which is believed to be what the mountains on Pluto are made of, and in smaller quantities, carbon monoxide ice. Now there are parts, regions of the surface where Pluto looks red, reddish. And this red color comes from compounds that are called tholins, Tholins. They are often found on cooled bodies with a high ices component, such as Triton, a moon of Neptune. Tholins are big, complex organic compounds that appear when molecules containing methane or ammonia or nitrogen are irradiated, especially by UV light or cosmic rays, such as the ones the Sun sends out. Tholins are not a precise type of molecule, and we don't need to go into the chemical details of them, but these compounds have a reddish-brown hue that could make them look like rock from afar, but they are not. And tholins matter because they are a prime example of organic chemistry in space. Their presence on Pluto or on Triton, or on other bodies including asteroids, illustrates that chemical processes triggered by sunlight or rays happen in very cold and distant environments. Tholins have been replicated in labs by irradiating mixtures of methane, nitrogen, and other gases. And this is potentially relevant to astrobiology, the search for the possibility of life in other locations than on Earth. Relevant because if complex organic molecules can form in such environments and can travel through space, this could be a mechanism for the appearance of not life itself. Organic compounds are not life, but they are bricks, constituents, or necessary steps for the appearance of organic life forms. Tholins traveling in space, arriving on planets like ours, this could be a mechanism that helped life emerge from simpler molecules. In any case, tholins are what gives regions of Pluto their reddish color. But not all is ice and tholins at the surface. There is also dust mixed with other elements, forming a layer of material called regolith. Regolith, from Greek, it means literally blanket of rock, is a fragmented layer of material, a mix of dust, soil, broken rock, and other fine particles, including ices. A layer that covers the surface of many rocky bodies. The Moon, Mars, asteroids, and also Pluto are covered in regolith. So the composition varies, and regolith on the surface of rocky bodies forms from different things. It can come from meteorite impacts. When a meteorite crashes on a rocky surface, it creates fine dust and debris. A big part of the regolith on the surface of the Moon, for example, resulted from impacts. Regolith can also appear on bodies that are exposed to extreme day and night cycles with big changes in temperature. This can fragment, break rock, and turn it into pebbles or dust. Another source of regolith is volcanic or cryovolcanic activity. Cryovolcanic, that is to say, cooled volcanoes that do not eject lava but ices. Cryovolcanism on Pluto probably contributed to deposit icy regolith at the surface. And finally, as these dusts and fragments are on bodies without an atmosphere, or with a very thin one, exposed to solar wind and cosmic rays, they get chemically modified with time, like for the tholins I discussed before. And these are the reasons why Mars, the Moon, other satellites in the solar system, or Pluto, end up covered in this material that can range from powdery dust to gravel-like fragments, depending on the body and its history. One of the many elements that were discovered, thanks to the New Horizons mission, is that the regolith on Pluto is dynamic. It is not just a layer that has accumulated over time, like on the Moon, but instead it changes constantly due to sublimation, the transformation in gas of its icy volatile components when Pluto gets closer to the Sun, as we saw before, or due to cryovolcanism. So even though Pluto is plunged in the dark, very far from other planets, and unlikely to harbor life, with its extreme cold, it is not completely inactive. Things constantly happen at the surface. Pluto might be way smaller than Earth and smaller than the Moon, but it has more natural satellites. 5 are known, and only the largest, Chiron, was discovered by ground-based telescopes. The 4 others were spotted by the Hubble telescope since 2005. Chiron is proportionally large for a satellite. It has half the diameter of Pluto and 12% of its mass, which is enough for their common center of mass to be outside Pluto. So technically, Chiron is a satellite of Pluto because it is smaller, but both bodies orbit around their center of mass, their common center of mass, and sometimes they are considered together as a binary system, like a double planet or a double dwarf planet in that case. Chiron was discovered in 1978, and it is tidally locked to Pluto, which means the same sides of Pluto and Chiron always face each other, like for the Earth and the Moon. Chiron's composition would be broadly similar to Pluto's, but probably without a subsurface ocean. The other satellites are smaller and not massive enough to be turned into balls by a hydrostatic equilibrium, this mechanism I told you about before at the beginning, the mechanism that makes larger bodies adopt a spherical shape. So the 4 other satellites are irregular, and they were invisible from Earth. They were discovered after 2005 by teams working with the Hubble telescope. They have been named Styx, Nix, Kerberos, and Hydra. Their composition is thought to be dominated by water ice too. We saw that Pluto's orbit was elliptical, but also tilted, meaning that it is not aligned with the plane of the solar system. And this raises another question. When you look at representations of the solar system, planets are all located on a two-dimensional plane, like a flat space that makes the solar system look like a disk rather than a sphere. And the same type of plane, of arrangement, seems to be true for other systems observed, or even for galaxies. All these systems look like disks. They are way wider than they are thick. This planar arrangement is not perfect though. Planets can typically have orbits that slightly deviate from the plane. The plane also called the ecliptic in the solar system. And sometimes they deviate more. Comets often deviate quite a lot, and so does Pluto, that deviates by about 17 degrees. But why is that? Why do star systems and galaxies arrange on planes instead of being like spheres, for example? It has to do with the laws of physics, for a part, and their formation process for the rest. In physics, there is this concept of angular momentum, which we could define as the tendency of an object to resist change in its rotational motion. Once an object has started to spin or to rotate, it resists a change in that rotation. And one characteristic of angular momentum is that it is a conserved quantity. As long as no external intervention stops it, it remains constant. That sounds a bit theoretical, so let's take a look at a concrete example. Let's take a look at our planet. The Earth has at the same time orbital angular momentum due to its movement around the Sun and spin angular momentum. It rotates on its axis. The Earth does both things without an external intervention that makes it orbit the Sun or spin. It does it because it acquired these orbital and spin angular momentums billions of years ago. And since nothing has stopped it since then, there is no friction with air in space. It happens in the void, so it continues. Conservation of the angular momentum also means that if for some reason the Earth suddenly shrunk, it would also start to spin faster. Like when a figure skater pulls their arm during a spin. That makes them suddenly accelerate. They spin faster. Not because they are putting more effort into it. It happens automatically because the decrease in their diameter as they spin, when they pull the arms, in physics terms, the decrease in their moment of inertia, needs to be compensated by a higher speed, a higher angular velocity, so that overall their angular momentum, the product of the two, remains the same. In the case we are looking at right now, the angular momentum means that once a body has started orbiting on a given plane around a star, it will not change easily. It takes a major external event or influence to make it change plane. Not impossible, we have the example of Pluto, but uncommon. A massive object like a big planet is unlikely to deviate much from its original orbital plane. Now, this plane comes from the initial formation process of the star system. As we saw at the beginning, a new system starts as a disk, because when a large quantity of matter collapses on itself in a corner of the universe, when it starts to spin, it will naturally adopt the disk shape. The rotation expands it outwards and flattens it due to the centrifugal force. Now, all star systems do not have parallel planes. There is no up or down in space. Their plane will depend on the circumstances of their formation. But observation of other star systems indicates that the same phenomenon repeats itself. And galaxies, too, tend to have this disk shape, large and flat, because they also spin around the galactic center, a gigantic black hole that keeps the galaxy together with its gravitational force. And this is why planets, moons, asteroids in the solar system, all bodies that formed within it, from material from the protoplanetary disk, this primordial accretion disk, inherited its planar orientation. After millions or billions of revolutions around the Sun, planets are still on this plane today, with very slight deviations, which when they exist were caused by their history. Bombardments by asteroids, collisions, possibly the influence of external bodies. But they typically don't deviate much. Massive planets like Jupiter and Saturn actually shepherd smaller bodies. Via their gravitational influence, they force these smaller bodies to stay in the ecliptic plane, reducing any attempt at deviating from it. Over time, another phenomenon that reinforces the planar arrangement is that orbits in a plane are energetically favorable. A body that orbits far from the ecliptic experiences greater gravitational perturbations from other bodies, from other planets of the system. So it takes more energy to maintain this path out of the main plane. Over time, between collisions, a little bit of drag, of friction from residual gas in space, and gravitational influences from planets, all of this tends to reduce the tilt, the inclination of an orbit. It makes the body align more with the system's plane. So these are the physical constraints and principles, but there are bodies like Pluto with a significant inclination in their orbit, meaning that they travel in space successively above and below the ecliptic plane. As I told you, it is a 17 degrees inclination for Pluto, relative to the solar system's plane. This tilt, this inclination, must be due to external influences, and Pluto is actually not alone in that case in the Kuiper belt. Comets that originate from it also often have these highly inclined orbits. In the case of Pluto, this is probably a consequence of past collisions or major external perturbations, probably due to Neptune. The interactions between the two could have tilted the orbit. Neptune is a suspect, but not the only one. We are back to the hypothesis I mentioned before about the formation and characteristics of the Kuiper belt. It could be also a past stellar encounter, or why not this elusive Planet 9 that caused it. Pluto is not the only dwarf planet in the belt. There are a few others that were discovered in the years 2000. For example, Haumea, named after the Hawaiian goddess of childbirth. Haumea rotates very fast on its axis, which gives it a slightly oblate shape. Its surface is dominated by water ice, rather pure water ice, judging by its high reflection of solar light, its high albedo, as it is called. Under this icy surface, it probably has a rocky core, and Haumea probably had a violent history of collision to acquire such a fast spin. Its rotation, its day, takes less than 4 hours. It is the fastest known rotation of any large solar system body. Another dwarf planet is Makemake, named after the god of creation of the Rapa Nui, the people from Easter Island. Makemake also is spherical. It is smaller than Pluto and orbits farther. It takes 310 years to complete one revolution. It was 248 years for Pluto. Composition-wise, Makemake is a close analogue to Pluto. Yet another important body is Eris, named after the Greek goddess of discord. Eris is slightly smaller than Pluto, but more massive, and in average it orbits further, needing 558 years to complete its orbit. And its orbit is even more tilted, even more inclined than Pluto's, at 44 degrees of inclination to the ecliptic, versus, you remember, 17 degrees for Pluto. None of these bodies are really big compared with the planets and main satellites of the solar system, and I could list more of them, even though their precise composition and history remain uncertain. But they are all part of the Kuiper belt and remind us that the solar system doesn't end with the planets. There is another world beyond Neptune. But what is there beyond the Kuiper belt itself? Is it the void of interstellar space already, or is there something else? Maybe there is something else, something called the Oort cloud. It is named after a Dutch astronomer, Jan Oort, who proposed it as the birthplace of long-period comets in the solar system. Shorter period comets, the ones that come back more often, are believed to have originated in the Kuiper belt. But longer period ones, such as the Hale-Bopp comet that takes 200 years to orbit, would have to come from farther. Hence this hypothetical cloud of objects. It would have formed early in the formation of the solar system, 4.6 billion years ago, when leftover gas and dust from the protoplanetary disk would have been flung out by gas giants, Jupiter and Saturn, and possibly other influences, other stars or other undiscovered planets like Planet 9. Due to the extreme distance from the Sun and the multiplicity of influences, including from bodies that were not on the ecliptic plane of the solar system, this matter would not have spread on a disk like the Kuiper belt, but instead adopted chaotic orbits, formed a cloud like a giant sphere, a bubble enveloping the solar system at a huge distance. Here again, the orders of magnitude are mind-boggling. I told you earlier, the Earth is at 1 astronomical unit from the Sun. Neptune is at 30 astronomical units, and the Kuiper belt stretches from 30 to 50-60 astronomical units. The Oort cloud, this spherical bubble around the solar system, would be between 2,000 to 100,000 astronomical units. The distances are on another order of magnitude. That's up to 1.5 light years, nearly halfway to the nearest star, Proxima Centauri. So the cloud could be gigantic, but not dense at all. The trillions of small and medium-sized bodies that would belong to the cloud would have a combined mass of only 5 to 10 times the Earth. Scattered on such a vast expanse, it really is not much, and the cloud would be very faint. I speak of it in the conditional because it is not proven either. It is so far, its objects are so faint that we never saw it, so we cannot be sure it exists. Its existence is a hypothesis created or inferred from the existence of certain comets and their paths, combined with formation models of the solar system that indicate its existence is possible, not necessarily likely, but possible. No spacecraft, not even New Horizons, that visited Pluto, has gone that far. And so for the moment, this distant, icy frontier remains full of secrets about our solar system's present and past. We have reached the end of our exploration journey for tonight. You can now let go and fall asleep, or if you are not sleepy yet, pick another story from my library. I'll be back soon with a new one. And in the meantime, sleep well, sweet dreams. Au revoir.